Good morning, everyone. It's an utmost honor and pleasure to welcome you all at the Foundation Day meeting from Center for Human Genetics. We at Center for Human Genetics are very happy to be hosting this meeting, and after such a long time of COVID outbreak, it's really a happiness and utmost pleasure to be seeing you all face to face. Without delaying further, Professor Balasubramaniam would be able to hear me. I'd like to invite him. He's the chairman of the governing board at Center for Human Genetics. He's a distinguished scientist and a director of research at L.V. Prasad Eye Institute, Hyderabad. A recipient of the National Order of Merit at France, honored by the government of India in 2002 with the Padma Shri, the fourth highest Indian civilian award, and he has contributed in popularizing science by writing columns in various newspapers like the Hindu and the Times of India. Professor Balasubramaniam, I welcome you, and maybe Nirmala can help with the online going on, please. Sir, would you like to please unmute yourself?
Am I okay now?
Yes, sir, you're audible. Thank you.
Good. So do I give my talk now? Oh, again.
Yes, sir, we are all eagerly waiting for your talk.
Okay. May I give my speech now?
Yes, sir.
Okay. Very happy Foundation Day to all of you at CHG. I'm sure that during these 2 days, you will not only be discussing the achievements of you, faculty, students, and collaborators have made during these years, but also the plans you have set out for projects you would like to work on. Let us recall those days when CHG had just started. The state of Karnataka has been offering solid support since the birth of CHG over 20 years ago, and continues to do so. The founding society of CHG had a group of eminent scientists like Professor Obaid Siddiqui, policy makers like Dr. Arkat Ramachandran, who was the former Vice Chancellor of Madras University and Under-Secretary General of the UN Center for Human Settlements. Dr. S. Ramachandran, he was the founder secretary of DBT. Then the economist, D.M. Nanjundappa, who was the Vice Chancellor of Bangalore University and also of Karnataka University. and of course, philanthropy from Dr. Kiran Majumdar-Shah of Biocon. Thus, within the short period of 20 years, CHG has grown to its current size because it has been serving a national need in genetics. I still wear the t-shirt you people gave me, which says, "Genes are destiny." Over the years, while the state government has given you the appropriate boost to your activities over these years, national agencies such as the CSIR, DST, DBT, ICMR, and the DBT India Alliance have also come up with grants acknowledging the superb work that CHG has been doing since it started 2 decades ago. And I am honored to be the chairman of the governing board. I've been coming over often to meet and listen to your work, and I've also shared some tasty food with several of you during the lunchtime in your canteen. It was very nice of your director, Dr. Jairam Karandale, to send me the book, Center for Human Genetics, or CHG, this one. Besides the articles by Professor Sharat Chandra and Vidyanand Nanjundaya, the book describes Jairam's work on the golden hair syndrome, Prader-Willi syndrome, and multiple myeloma. And Dr. Meenakshi Bhatt was one of India's best-known clinician scientists and a leader in her work on rare diseases. Describes not only the work on Gaucher disease and glycogen storage disorders, where she not only identified and diagnoses patients, but also offers them low-cost medical diets with a company supplying the components. This, I think, is very important. You call the patient, address the patient, examine the patient, and so on, and after you find out, you also try and offer the treatment mode by working together with the company right there. One of the photographs in page 6 of the book, I'll show you that thing here. Look at this photograph. The book has a group of participants from across the country at CHG's Rare Diseases Awareness Day in 2018. Swati Shetty works on prenatal screening of retinoblastoma. Gurudatta works on fruit fly models for genetic mutations. Anuranjan Anand on hearing disorders, not on the flies, but on people. And an item of particular interest to me, since I am hard of hearing. I'll be online on both days and look forward to hearing all the exciting things we'll be discussing during these open days. Thank you all, and have a nice day.
Thank you, sir, for giving us a nice overview of Center for Human Genetics.
Yeah.
And with this, I would like to now request Nirmala to play a video which Dr. Kiran Majumdar-Shah, our member of governing board at Center for Human Genetics, has been kind enough to send us this video. With this, I would also like to share that she has been recently elected as the Fellow of the Royal Society of Edinburgh, which is one of the world's most oldest and most respectable academic societies. Nirmala, please play the video. Thank you.
I would like to start by congratulating the Center for Human Genetics, which has been the brainchild of Professor Sharat Chandra and so ably steered by Meenakshi Bhatt, Jairam, and many others, including, of course, the illustrious board chaired by Dr. Balasubramaniam. I do believe that this is a world-leading center, a center that's making a huge difference for the study of rare diseases, and which is actually helping families and patients who unfortunately are afflicted with rare diseases. I am particularly impressed with the tremendous progress we have made at CHG, both in terms of understanding the disease at the genetic genomic level, understanding the disease at a metabolic level, at a biochemical level, and of course trying to develop interventions that can help these patients and families deal with these rare diseases. I know the singular devotion that Meenakshi Bhatt and her team have had to patients and families who have to deal with these diseases. And I'm particularly grateful to them for also helping to develop an ecosystem of specialty foods that can help rare diseases, diagnostics that can help with diagnosing these diseases, and doing many of these studies in rare diseases that can throw more insights. What we now need to do is to focus on developing therapeutic interventions in the form of enzyme replacement therapies and other such therapies that can hugely impact these diseases in a way that quality of life is improved. I have attended many programs where we have seen young patients and their families come forward and share with us their experiences and their debilitative health conditions, which really is very heart-wrenching. Equally, we've also seen how compassionate care provided by many companies that develop enzyme replacement therapies is helping many of these patients. I'm also happy to see that some positive developments are there in the form of policies, in the form of financial support, etc., but we need to do a lot more. And I would like to see CHG playing a key role in shaping the policy to a much more advanced level. I think Ayushman Bharat itself needs to have a much greater focus on rare diseases, both in terms of diagnostics, treatment and prevention in whatever way is possible. I would like to really commend all the research that is being done, the papers that have been published, the patents that have been developed, etc. But one thing that I would like to see happen in this country is for low-cost enzyme replacement therapies to be developed. And in that, I think we need a commitment from the government in terms of buyback, in terms of a price support, and in terms of incentives that companies can avail of in developing these urgently needed therapies. I wish the Foundation Day programs all success. I know you have an excellent lineup of speakers. I know that there is some very exciting poster sessions and sessions with students. I wish I could be there, but I have various conflicting commitments which prevent me from being with you in person. But I really wish the Foundation Day all the very best, and here's to celebrating many more milestones in the future, many more Foundation Days that keep celebrating successes and the tremendous impact that they're making on society at large. Thank you. I would like to start
So, thank you so much, ma'am, for your words and best wishes. As Dr. Kiran rightly said, CHG has been the brainchild from Professor Sharat Chandra, and he doesn't need any more introduction. He is there here with us, and I would like to invite him to please welcome all of us with a welcome address. Thank you.
I've been given the task of welcoming all of you, and I do so wholeheartedly. I noticed that most of the people who have registered for participating in this two-day function are students from neighboring institutions primarily, and a small number of very distinguished senior people. So most of what I wish to say is directed at students rather than at the senior people who are all familiar with the obvious facts. Now, but I have a few things to say to the senior people as well, because many of them sit in policy-making committees, they act as advisors to institutions and so on. So I have some general I wouldn't call them complaints, but general matters which I think should engage the attention of such senior people as well. And maybe I should start out by listing some of these concerns I have. One of them being, when we started CHG and wanted to introduce specialized education in human genetics in relation to disease, we encountered a lot of problems. Among them, this huge divide between science on the one hand and medicine on the other. They have grown in the last, let's say, a century or more in this country as silos, as parallel entities, with their own system of regulatory mechanisms, and there's hardly been any crosstalk between these two arms of knowledge, because there is no need to in many cases until very recently, because of infectious diseases like COVID, for instance. But much before that, because of genetics, really, that's the one that's pulling the two together, inevitably. When you look at the size of these entities, the silos I mentioned, science is a huge enterprise in India, and so is medicine, of course. But these were not this huge even 25 years, 30 years ago. When Karnataka was still the state of Mysore, there's only one medical college for all of Mysore, and it admitted 50 students. So it is a choice thing to go to a medical college during the old days. But today, by last count, I am told that there are 600 affiliated colleges to Rajiv Gandhi University of Health Sciences. In other, there are 600 medical colleges in the state of Karnataka alone. And the number of students they admit is over 100,000. And the task of regulating these many curricula, these many colleges and so on is next to impossible. So when one wants to introduce something like genetics into these curricula, it's a tremendous problem. And we encountered these problems because we were trying to run a course which is bridging these two, science on the one hand and medicine on the other. anyway, we have succeeded to some extent, as Meenakshi and others will probably tell. And we do conduct 2 courses, one of them in human disease genetics, and many of you are enrolled in that course. And the other is on pediatric genetics. It's an 18-month course, recognized by the university, and admission itself is done by the university. It's a highly competitive course. Only 2 people are so admitted on an all-India basis. Why I say all this is because it's time that institutions of higher learning in science start giving employment opportunities for medical doctors as faculty, not as giving occasional lecture on the current disease or whatever. Similarly, I think medical colleges and institutions must make appointments to scientists as regular faculty. I'll just give one statistic. The country's top 10 scientific institutions, you list them. Among them are 3 right in Bangalore. And insofar as I know, there's not even a single medical doctor in any of these 3 top institutions of the country. And if there is one, he's doing E. coli biology or something like that, unrelated to human genetics, and he doesn't see any patients. There is no hospital in any of these 3 institutions, other than a health center, perhaps, where some simple medicines are dispensed by the doctor. So what I'm trying to say, there must be much more meaningful involvement at the faculty level. And if there is not even a common ground on which they can sit and talk, common canteen and so on, how will the collaborations develop? And at the heart of human genetics is collaboration. No single man can understand the subtleties of the phenotype of genetic disorders, and because scientists cannot appreciate those. Similarly, the clinician should not be a mere supplier of material to the scientists to investigate. There must be substantial involvement in each other's research. And I believe this is one of the reasons why we have not really made a major impact in research worldwide in what you might call human genetic biology. And that area is now everywhere, from evolution, origin of man, current epidemics, and genetic susceptibility to disease, and so on. So it's very, very important that we bring together, and I say this primarily to the senior advisors here, who they must make it. It's not just saying, yeah, these things ought to be done, but making sure that the next appointment in the top institution is a doctor who actually sees patients half the day, or at least on alternate days or something, so that there is a direct feeling for the problem. We see this all over the world, and whether it's Harvard or Stanford, the medical school is right there. And it's very easy to walk over and build a collaboration of like minds. Yeah. Coming to the students, I think those of you who are entering this area, this interdisciplinary area, have tremendous opportunities. Challenges, of course, are there, but there are also opportunities which a student 30 years ago wouldn't have had, because this field didn't exist really in any real sense 30 years ago. A student today can participate, especially with strong science background, if he or she has, in developing therapeutics, as Kiran Majumdar said. And there's so many new things waiting to happen But one of the things that this center has done, of which I am particularly pleased, proud, is that it has actually developed therapies, low-cost therapies, which are in use, approved by FASTG and other national bodies. And that is the kind of research I think is not only helpful to the patients, it's very fulfilling to the person who participates in it. One of the great things about being in human genetics is you're actually assisting or helping a family in distress. And as all of you know, a genetic disorder in a family causes complete disorientation within the family. They do not know, they're bewildered, they don't know how to deal with these disorders. They know that some relative has had some distance, but when it happens in one's own family, it's a devastating experience. And the family isn't the same anymore from that day they get this diagnostic. And so I suggest to the young people that in all that you do, keep this possibility of a therapeutic approach to a particular disease that you're currently thinking. The other is counseling. Now, there's a worldwide shortage of genetic counselors. Now, with your training in genetics and the counseling skill, you can do far more good to the world than by, I would say, than publishing one more paper. Okay. We have also tried to incorporate I should say, my colleagues have tried to incorporate an ethics module into the program, the Human Genetics MSc program. And if you just go and watch one of those sessions, you'll see how much, the human drama in that family, okay, regarding that one child that they had is really very touching. The other thing is, in counseling, you must develop good communication skills, careful use of language. Not everyone starts out with those skills, but you must cultivate those skills. Those skills are widely necessary in science, not just in genetic counseling. And I would urge all students who are here to make a special effort to develop communication skills, writing skills and speaking skills and communication with the other party. And usually doctors tend to be better at it than scientists. Scientists are much more comfortable writing in the papers in the privacy of their rooms. But a doctor necessarily has to see the family in distress and do whatever that can be done. I just had prepared a few slides. I hardly have anything more to say on this occasion. Well, I request Suna, whoever, to show these slides quickly, if only for... you can remove this. Next. Well, that particular statement by Lalit Sangvi, who was a pioneering human geneticist of this country, I put because he was thinking even 50 years ago what kind of approaches are possible to reduce the prevalence, the incidence of genetic disorders. And one obvious doable approach seemed to be to reduce the number of first cousin marriages, closely related marriages between closely related people. But he also said, based on his experience, that no aspect of Indian society is as resistant to change as the institution of marriage. there's sort of a stranglehold. Everybody gets into the act of arranging a marriage. People who are unrelated to the family are also getting into the act. So this is a very, very difficult aspect of Indian society, and unless you change that and give some freedom to the people who are actually getting married, obviously it's not going to happen. So this is not strictly related to what I said earlier, but it's an interesting comment by a pioneer human geneticist who he did a lot of field work, and based on that he made this statement. Please, next slide. Yeah, about this is a well-known thing, of course, I mentioned. Go ahead, next slide. This is where I really should begin. Penrose in 1966. 1966 was hardly 10 years after Chio and Levan had discovered the correct chromosome number of man. He delivered the presidential address of the Chicago Human Genetics Congress, International Congress. There he made this comment, saying that human genetics has grown into one of the most complicated and demanding disciplines in the whole of science. Now, this was in 1966. I wonder what he would have said if he had written this today. This has become unbelievably more complex, and there's no aspect of human society that human genetics doesn't touch, although we don't realize that this is at the root of all that are genes. Next slide. And Crick in 1993, this is just when the idea of mapping genes, cloning human genes was being discussed. He said that the impact of modern genetics on medicine will be big in the next 5 years, and in 10 to 15 years it will be overwhelming. And of course it's come true today. Next slide. Well, Victor McCusick, who is sort of godfather of medical genetics, at least in the US, said the practice of medical genetics and of genetic counseling, I put this slide because of his emphasis on genetic counseling as early as 1996, in particular will become the medicine of the future and the responsibility of many, if not all, in medicine and allied professions. Next slide. Well, I just want to review some of the things that Meenakshi and Jairam have said in the brochure and elsewhere. What pleases me most is in the last 10 years there's been an upsurge of interest in genetic disorders, usually under the title rare diseases. And the CHG has played an important role in building public awareness, in assisting patient support groups, and in deposing before courts on behalf of patients. Importantly, CHG has assisted the government at the center and the state in drafting rare disease policies. So CHG has been a part of the drafting committees, members, Meenakshi in particular. Next slide. And our education programs has drawn sufficient attention and for its quality, with the result that I thought I will make this one point. UK Medical Council allows medical genetics interns to get trained for a month or more at CHG and obtain credit for it towards the certificate given by them. Okay, so this is an acknowledgement of the quality that prevails in these teaching programs. Next slide. And broadly, CHG's public lectures and short-term training programs attract a large number of doctors, scientists, etc. Workshops on new technologies are being held twice a year on average. Over 500 MBBS, MD, and BSc, MSc graduates and PhDs have received such short-term training at CHG for periods ranging from 2 weeks to 6 months. Next slide. This is, of course, is a big problem. Lack of recognition, diagnosis of genetic disorders at an early stage of there are disorders where the child is all right for 2 years, 2.5 years, 3 years, and then suddenly the onset of the disease begins with no prior clue And in so many other, as in so many other disorders, early diagnosis is the key to reasonable treatment, successful treatment. And one of the things that is badly needed here is to train doctors to recognize genetic disorder. If it's a very rare disease, you would not have seen patients of that type before. And this is one major avenue for reducing the incidence of the genetic burden on the population is to early recognition and wherever possible therapy or ameliorating the disease in some way and so on. So early diagnosis is very important, especially for doctors. And we do have training programs and short-term courses, etc., for that purpose. And as mentioned, the recognition of genetic disorders early can help prevent irreversible brain and organ damage in affected children. There are opportunities for translation, such as in developing local diets for patients with phenylketonuria, organic acidemias, and certain glycogen storage disorders. Most of these products allow both on-site and online support in setting up the laboratory. Jairam has spent a lot of time and effort on this particular. Any other slides? That's it. So this pretty much sums up what I wish to say.
Good morning to you all, and I'd like to welcome one and all for the Foundation Day ceremony, and this is the first day scientific session what we have started. I'm going to brief you about the diagnostic activities what we have at the center, mainly concentrating on starting with basic cytogenetics, what we call conventional cytogenetics, and move into molecular cytogenetics, what we are doing, and finally show the molecular genetic aspects, what diagnostics, what we are doing, as well as we are reporting out these cases for the in-house patients, as well as to the outside patient samples, what we receive from all over India, from Karnataka as well as from other states. And to start with, we have started the diagnostic facility way back in 2003, where we started doing conventional as well as molecular cytogenetic fish-based diagnostic services. And most of the tests what we started doing, they were all free to start with, to make the doctors comfortable. And there were many questions asked at that time, whether the fish-based diagnostics what we started as prenatal were really working or not, because it was in 2003, nobody was believing. So we had to take a chance and make them trust us. To what extent, whether it is 99% or to 100%. That's where we proved, starting from a big hospital in Bangalore, and where they were doing routine prenatal procedures. And we were doing fish aspects to detect all these genetic diseases which can lead to live birth. For example, 13, 18, 21, X and Y, trisomies for these chromosomes. And we were doing the fish aspects and reporting it within 24 hours. And they were doing the culture and proving the same thing after 15, 20 days. When the results correlated nearly 99.99%, they couldn't believe it. Because somewhere we had to develop the protocol and convince them. That's where we started. It took almost 1 year. The same way we started doing the cancer diagnostics, for example, CML, and the protocol itself has been standardized in St. John's because we had a doctor, Dr. Rajesh Behal, who was practicing there part-time from the Center for Human Genetics, and he knew the protocol to be adapted, and he started straight away in 2004. And straight away we started doing the fish. Within no time we were giving the results. Those patients which could go directly for the targeted therapy if there is a genetic marker which is positive in that patient. So Philadelphia chromosome was detected at that time by fish. That was the beginning in Bangalore. And slowly what we did is, we started training people, training doctors, training scientists, training laboratory heads in this area of fish-based diagnostics. And we started doing these basic conventional cytogenetics as well as fish to start with free of cost. And conventional means, doing karyotyping. We started for the patients who are coming from poor background, that is the BPL families from publicly funded hospitals. We did it free. And for the affordable patients, we were charging at cost. Because private players, they were charging heavily. That's why even the doctors who were moving away from the tests, they were avoiding the tests. Now, we have analyzed and reported around till now, from 2003, I can say that we have reported around 50,000 samples, and which includes prenatal, postnatal, and cancer diagnosis. Diagnostic mainly by doing conventional cytogenetics as well as fish-based, different kind of fish what we were applying. And we were applying for the, these chromosome breakage studies, which are precancerous, in the different kind of syndromes like Bloom syndrome, Fanconi anemia, all these things, which was not done in any of the commercial laboratories. We were the first people to introduce, and that went on very well. Even now we are the people who are doing it, and we train people. People come all the way from Delhi to get trained, and they do their PhD work here. And that was the plus point in standardizing the breakage studies. To tell you the gold standard, what we use is called GTG banding, Giemsa-trypsin banding on human chromosomes. We arrange these chromosomes, and this is a metaphase chromosome, which has 46 chromosomes in it, which looks under this is the way it looks under the microscope after we band it, and then pair and then make the karyotype. And this remains gold standard even now. So no other molecular aspects can reach to this kind of results. What this gives a result which is perfect. And I will give you some examples which no other technique, we have molecular technique can give you the answer, straightforward answer. And this takes very few, the amount of money what you are going to spend is peanuts in front of the other molecular tests what we pay so much money. And to start with, everybody we recommend that you start with basic karyotype. After you go for anything you want, to prove further. So that's how we started doing this. For example, if you see this karyotype, you can see this mother. This mother is a carrier for chromosome 1313 translocation. She either have a pregnancy loss in future pregnancies, or she will have a child which is going to be abnormal and which can lead to live birth, but it can live for 1 year maximum. See, this is the advantage. This, in any other technique, molecular technique, it shows you the genome is balanced. You won't find this kind of balanced translocation found out by any molecular technique. But this simple technique, karyotyping itself, you can make out. Now, the other one, if you see, it has this is the Down syndrome karyotype, where you have 3 copies of chromosome 21. This has happened because the mother is a carrier like this for chromosome 21 translocation. She is fine. She doesn't show up anything, but each and every pregnancy, 100%, she is going to have a Down syndrome child. If you have not analyzed the mother, immediately after giving birth to this child, every pregnancy will lead to the trisomy 21, which is the Down syndrome. So these are the simple things which can give you the best answer, and these are all going to be helpful for the doctors to counsel the patients properly. If they don't come to counseling, if they escape from counseling even after having an abnormal child, and they will have the same problem again and again. So multiple pregnancy loss or abnormal children is the result of that. Like that, consanguinity, what we have been spoken just now, in India is known for consanguinity. Uncle-niece marriage is so common, and first-degree marriage is also common. Now, if you see this karyotype, both husband and wife has the same translocation. Husband has a translocation between 8 and 9, 19, 8 and 19. Even the wife has the same translocation, 8 and 19. There is no way they can have a normal child. So this is the first-degree cousins who married each other. So this is one way of detecting how the consanguinity is running in the family. And basically, spending a small amount of money, you will come to know the reason behind this. If you see this karyotype, it need not be consanguinity alone. Multiple pregnancy loss can be a result of translocations in either one parent or both the parents having the translocation. Means this couple, the husband has a translocation between 5 and 18, but the wife has a translocation between 2 and 18, unknowingly, unexpected. These are all de novo. And they will also experience the same pregnancy loss. They will not have any normal children. So these two parents, cases, they had to go for IVF pregnancy. They had to go for donor eggs. That's the only alternative what they have, and they chose. But for counseling, if you don't have this kind of results, how do you counsel these patients? So doctors are the ones who get benefited from this kind of simple tests. Now they have the reason to give and tell them and counsel them properly using these results. And if you see this one, very, very rare case, it can happen only in India most probably. And this is the only 1 or 2 cases been reported all over the world. Now you can see the husband, the normal karyotype, he has only 44 chromosomes. But he is homozygous for Robertsonian translocation. Both chromosomes are translocated. 13, 14, 13, 14. 14 is sitting on 13. It is easy to have this kind of translocation, 13, 14 translocation, who is a carrier. This individual is normal. This individual is also normal because he doesn't have both the copies of 14 here, sitting here. But it is tagged to chromosome 13, translocated to chromosome 13. We call it as Robertsonian translocation. But the wife is a carrier for 13, 14 translocation. How did this happen? This is running in this family. Big family. Many people are carriers for this. This one, they married each other, cousins. This is the consanguineous couple, and they are experiencing pregnancy loss. Each and every pregnancy is abnormal and lost. And this kind of case you won't see often. The other cases, whatever I have shown, that may be there. But this is very, very rare. And that's how I'm just showing that this kind of abnormalities, nobody would have picked up unless you have done a karyotype. This, in genome analysis, any other technique, it would have shown normal, balanced. So everything is fine in this one. Even NGS or whichever technique you use, microarray, that will show that it is balanced. It's fine. But what happens to the pregnancy loss? There is no answer for that. So basic cytogenetic technique, conventional cytogenetic, answers many of your questions by not spending too much money. That's what I'm just trying to mention this. Now, I was mentioning about breakage studies. Now, we have done maybe more than 200 cases of breakage studies alone, other than the research work. Now, for the diagnostics, this is the way we are doing. You can see the breakages. This is a child which has this many breakages, which has been referred for the Fanconi's anemia. And the same thing we extend it to the Bloom's and then ataxia, other syndromes also. And this is one of the way it looks like chromosome break as well as chromatid break. They have both breaks, chromatid alone or chromosome together. Whole chromosome is broken like this, or only chromatid is broken like this. Now, another way of looking at it is to prove further if it is in the second stage, this will lead to this kind of radial arrangements of chromosomes. The stickiness of chromosomes, all these acrocentric chromosomes stick and form a radial arrangements like this or this way. So that's another way of proving this. These are the breakage syndromes, which we often do it for many cases, which is more frequently sent to CAG for this purpose. After the showing you a few slides about the conventional routine cytogenetic analysis, what we do, I want to show this fish diagnostics, what we started back, in 2003. We started conducting workshops in that year itself, 2004 itself. And we were getting specialists from various different companies, as well as specialists from who were doing routinely from US also. And started doing basic fish techniques for the prenatal, for microdeletions, as well as for cancer. And started training people from different hospitals, scientists, and then doctors also. And we extended the same thing to further in the later years for spectral karyotyping, where we paint the human chromosomes in 24 different colors, multicolor fish, as well as multicolor band, which I'm going to show a few slides. And we started doing these workshops on a regular basis every year. Till now, we have trained more than 500 professional doctors, scientists, laboratory personnel, researchers from various hospitals, diagnostic centers, and from research institutions. Now, to give you a basic idea that how we do the prenatal diagnostics, where we accept sample like amniotic fluid, chorionic villi, or fetal blood. This is the way we started doing the prenatal diagnosis of trisomies, which can lead to live birth, 13, 21, 18, X and Y, which is very important, and it is must. And all other chromosomes we cannot, mainly because we had to suspect. Because of the genetic markers, we start testing these 5 chromosomes. This is for 13, 21, red for 21. You can see easily 3 copies of 21 here. This is the nucleus, 1 single nucleus, and 2 copies of 13. Like that, we can check for 18, X, Y. And you can see the result of this one. This is a trisomy 21, which leads to Down syndrome. Prenatally, we can diagnose like that. Even the pregnancies, which even the scan is too early to detect, the triploid fetus, how it looks like, we can detect using the fish probes. So this gives signals like only 1 chromosome, 3 signals. Here you can see for all the chromosomes, 3 signals. If you later on, you can culture and see this is a triploid fetus, which can last for 6 to 8 months. Second trimester itself, it will be lost. Pregnancy loss will be happening. And this is the way that, once the family is facing the trisomy fetus, first child is trisomic for Down syndrome, for example. Next future, following pregnancies, they want to check prenatally. This is the way quickly we can, within 24 hours, we can check and tell the results. Later on, you can go for confirming the results by culturing the cells, which usually we do it. So fish, I usually say that it's an adjunct to conventional cytogenetics. And for, later on, in the same year, we extended the fish studies for microdeletions. For example, this is the DiGeorge syndrome, where these children will go for correcting their problems with the heart. Before the surgery, they come to give the samples for the genetic studies using fish probes. This is the fish probe for chromosome 22, and this is the locus where it has to hybridize the particular probe. And this patient, which is positive, which doesn't show that red color here. This is the normal, this is the abnormal. This is how we confirm microdeletion syndromes. And these are the ones which will go through the counseling, and this counseling, during the counseling, doctors will convince them immediately after correcting the problems with the heart, correcting the surgery by surgery, later on down the road, 3 months later, 6 months later, 1 month, 1 year later, how to manage the patients. They need not come back to the place where they have done the surgery. So prior to that, they can counsel and educate them properly and manage the patient properly. So this is the one where we use the paint probes to further prove and detect the abnormalities like translocations, insertions, and finding the markers, all those things. For example, this chromosome, what you see here, is the chromosome 15, which has derived material from chromosome 6. You can see here, this is called insertion from chromosome 6 to chromosome 15. So this goes alone to the child, it becomes abnormal. This is the father which is a carrier for this. We have come back to study the father. So the child which is born, which is abnormal, had only this pair, this chromosome, abnormal chromosome 15, where we have the trisomy for the part of chromosome 6. Because of that, the child was abnormal. So that's how we can prove using different kinds of probes and further prove the genetic problem in them. So to give you a quick example for cancer, the hematological cancers, the famous chronic myeloid leukemia, which has Philadelphia chromosome, which is the result of translocation between chromosome 9 and 22, Philadelphia chromosome. We can develop the probe BCR, ABL, BCR and chromosome 22, ABL and 9, hybridize, and then see this uncultured, this is done on the bone marrow sample. And this is the positive Philadelphia chromosome showing in yellow signal. The combination of BCR, ABL is in yellow color. Otherwise, BCR is in red and BCR is in green, ABL in red. Combination of that, if it is positive, the marker chromosome, Philadelphia chromosome, shows up in yellow color. So without culturing, immediately we can check. So these patients can go through the targeted therapy. They need not wait for a week time to start the treatment. And this is the chromosomes where it is showing that this is the Philadelphia chromosome. So many of the prenatal probes, as well as these probes, whatever we are showing, we have developed in-house to start with in way back using ICMR funding. And we developed several of them using by buying the clones and labeling them and then hybridizing and standardizing here itself. As well as we were using the PRINCE, primed in situ labeling, to develop several probes for different chromosomes for the repeat regions, centromeric, telomeric, all these things we were doing, as well as the heterochromatic regions of the different chromosomes, including Y chromosome. Now, to go further, we didn't stop there. We extended our workshops and diagnosing solid tumors. This is the solid tumor, the breast cancer, where we do the amplification and look at the amplification of HER2 gene, which is going to be helpful for the targeted therapy in these cancer patients, breast cancer cases. This is a normal hybridization pattern. The HER2 is on chromosome 17p and 2 red and 2 green. And here you can see the amplified HER2 gene, which is on this section. These are all on section, not on chromosomes. So we get the sections, we do it, and then confirm. And if it is positive, we report out as positive. This can go directly further. This result will be correlated with the immunohistochemistry, that is IHC. And then the treatment will start. Because IHC will lead to a lot of confusions if it is 2+. That's the grade. So when it reaches 2+, definitely they send it for HER2 fish diagnosis, and then we confirm it. Then they can start the treatment. That is the advantage of it. Now, we started these things way back in 2003. In between, we started. Later on, we started doing high-end or advanced fish techniques. From 2009, we started offering second opinions for complicated cases like complex translocations, derivative chromosomes, markers, etc., using advanced fish like spectral karyotyping, multicolor fish, and M-band, multicolor band. And we get samples for second opinion from all over India. I'll show why it comes here. CHG is the only place where this kind of high-end molecular cytogenetic techniques are offered for both diagnostics and research. And this is the slide which shows the spectral karyotyping, where we are painting all the human chromosomes in 24 different colors. Now, you can see different variations in blue itself, green color itself. And when we do the karyotyping, it shows the abnormality. You can see this part of the chromosome has been translocated to this chromosome. So just by looking at the color, we can say that there is a translocation between 6 and 15. 6 and 15, yes. So without knowing karyotyping also you can detect. And why we had to use this technique, I'll come to that. You can see that there is a multiple translocation happening. If it is straightforward two-way translocation, it's easy to detect by karyotyping itself. We need not go further. If it is multiple translocations, for example, this one, this is a case with polycystic ovary syndrome. It's a coincidence. It's not a marker. There's a four-way translocation, exchange of material between 4 different chromosomes, between 1, 11, 3, and 4. No way we would have identified exactly that 3 has gone to 4 or 1 has gone to 9, 11. So that kind of confusion, the colors will detect. So when you paint with different colors, it will clearly shows that this material has come from 4 and this material has come from this chromosome, 11. So like that, it's so easy to detect if you have this kind of complicated chromosomal rearrangements. Now, in this case, this is a case of multiple myeloma, where you can see 17 to 20 translocations happening in that case. Not 1 or 2 translocations. No way you can do the karyotype and confirm that it's happening between 2 different chromosomes, 4 chromosomes, 5 chromosomes. But you can see even a single chromosome with multiple colors means it has derived material from different chromosomes. So, because of this spectral karyotyping, using different colors, we could identify, label, and make this karyotype like this. So this is the advantage of using multicolor. Even the M fish, what we call multicolor fish, is also similar to spectral karyotyping, but it comes from different companies, and the capture, everything is different. Now, if you see this karyotype, which is a multicolor fish, we call it as M fish, where we have abnormal chromosome 9. This is abnormal, normal chromosome 9. This is abnormal chromosome 9 having a duplication kind of thing here on Q arm, here on chromosome 9. We don't know, because till now what we have seen is exchange of material between different chromosomes. If the event is happening within a chromosome, there is no way we can identify using only paint probe. Now we have standardized, and we have conducted several workshops also, and we standardized this banding called multicolor banding for a single chromosome. This is the chromosome 9 having 12 different colors for each and every band. Now the same thing, if you put it on the abnormal 9, you can see that there is not only a duplication of the same segments, but it has inversion also. Inversion duplication is happening in this one. So that's the event, what is happening in this abnormality. So no way we could do it by regular conventional cytogenetics or by multicolor fish. So multicolor band is the only one which could retrieve the results. Now, in the similar way, this is the more regular way of looking at the isochromosome for X chromosome, which always it shows up in Turner syndrome patients. Either purely 45X is Turner syndrome. We call it as variant Turner syndrome when it has other abnormality, like it is missing P arm of chromosome X, but it is duplicated for Q arm of X chromosome. This is called isochromosome X. And we don't have any doubt, just by doing karyotype itself we can see. But when it looks, the other abnormal X looks different, like this. We have our own doubt that whether it is a abnormal iso-X or not. To prove that further, we have to do this kind of banding, which will show this is not a isochromosome for XQ. It is a translocation between X and X, which is very rare. X chromosome translocated X chromosome. So that is the derivative of this. You can see this. This is the region it has exchanged, translocated between two X chromosomes. This is the intact. This has happened during meiosis. So this is the abnormal X, and using multicolor banding, we could identify this and label it as variant Turner syndrome. And we could find out the problem having this kind of various problems having within a chromosome. So I think that's last slide for the cytogenetics. And we started molecular genetic services in 2006, and DNA tests for many human genetic disorders, and common as well as rare diseases also we have started doing tests. And Rastopathies and her team, they do all these tests at CAG, and especially those which are not available elsewhere in India, not for the regularly available tests we have standardized here. And based on the request from the doctors, they have standardized and started doing it. Those that are common and not financially accessible to a huge part of the population, like beta thalassemia, Fragile X, all these things, where other commercial labs charges so much, but here it is done at the cost or free of cost for the publicly funded hospitals and our own in-house patients. The tests are offered at free or at the cost. And it began in 2006, as I told you, and since then the load has increased so much. The requests have been increased, and different requests have come up, and we do different technologies that, like PCR based, Sanger sequence based, qPCR based, MLPA based, as well as NGS based. All these tests are taken care. We do it only for the rare diseases as well as based on the request from the doctors, and not for the routinely available cases, just to help the doctors as well as the patients. Now these are the small list of rare diseases which have been, we are getting regular samples for, Y microdeletions to Gaucher, beta thalassemia, glycogen storage disorders, and many more of them are there. And what we are doing is, another plus point is the prenatal diagnosis for the molecular test. What we have been done it for the parents of a affected child, as well as the affected child, since we know the mutation in them. In cases where we have confirmed the pathogenic variation in the parents for a serious disorder, Prenatal diagnosis is offered and maternal cell contamination is ruled out for such samples. We do both mutation tests in the pregnancy as well as we check the maternal contamination also, which is must. I think that's this is the clinical and molecular cytogenetic team at the CHG, and this is the molecular genetic team headed by Dr. Swati Shetty and Ambika, Tejaswini, Praharsha, and in my team Pooja, Soumya, Harikripa, Krishnamurthy, Priyanka, Arvind. These are the people who are working on this. And I just want to acknowledge the grants, the funding received from both ICMR and DBT, and the infrastructure support from the state government. Thank you very much.
Thank you, sir, for the overview about the various diagnostic activities in cytogenetics and molecular department. Going forward or backward, I don't know how to say this, but we need to cover the clinical activities that leads to the testing and then the post-test counseling. So may I please invite Dr. Meenakshi Bhatt, Professor Dr. Meenakshi Bhatt, and the Associate Director of Center for Human Genetics, to give an overview about the clinical activities at CHG. Over to you, ma'am. Thank you.
Thank you very much. And it's my talk between now and tea, so I'll just be brief and just talk about the things that we have been doing at this center. So around 2006, we started looking at rare diseases when rare diseases wasn't as glamorous and not many people were interested in it. In fact, there was a general discouragement saying that everything about it is expensive, whether it is diagnosing it, you can't do much once you have a diagnosis, and certainly there were very few treatments. Even today, there are only 5% of diseases, of the 7,000 or so known diseases, that actually have treatment. But by complete default, because we had set up clinical services and we were pretty much draining the entire country's, entire state and lots of the country also, and today we get a lot of patients from abroad also. We've realized that nearly 80% of disorders have a genetic basis, and the vast majority of them come in the pediatric age group, where parents are most concerned about trying to find an answer. And that's how the journey started. So from 2006 onwards, we started looking, and now currently when we look at our numbers, we have seen over 30,000 families over here with different disorders. One of the good things that we started doing was meticulously maintaining all records. We have all pedigree charts, clinical findings, clinical photographs where the patients have given consent, all the results sampling, and the non-genetic results also tabulated. All this necessitated that, in fact, the entire clinic area is filled with multiple drawers. And then now, since the last 2 or 3 years, we have invested in developing a database, which has been pretty much state-of-the-art, but constructed to our own requirements with a very small software team. And this has been revolutionary for us. The average patient care in government hospitals are usually people flocking without appointments, just squatting outside, waiting from morning to evening to be seen, just showing how desperate families are before they actually get seen. And on an average, we were seeing in the last few years about 2,000 to 2,500 new families a year. We're not talking about the reviews that come through. And this is a massive load, considering that we've got very few clinicians that can actually translate genetic results. All the complex results that you've seen has to be explained in lay language to the family onto what it means to the family. And then came March 2020, when suddenly there was a lockdown because of this whole COVID issue. But pregnancies don't wait. Prenatal diagnosis is required. Inborn errors need to be treated. If you have a sex determination disorder, the child has to be assigned a sex. And all these things were realized as emergencies. And 2 months into the lockdown, we started telegenetics. We were so surprised at the reach of the telegenetics, because we were using a Zoom app to connect, or WhatsApp to connect to families directly. And as remote as it may be, in the smallest of villages, sometimes in the field when they're harvesting stuff that we were contacting families. And we were able to reach out to at least 90% of the families that required these sort of counseling. The experience itself was so successful that we actually published it. So we saw about 1,000 families from May 2020 in the next 1 year. We could even diagnose dysmorphic syndromes over a telephone, which was subsequently confirmed. And this experience of ours was the only paper from a developing country to be published in a COVID special counseling issue. So we have continued this hybrid mode, some live and some in the same online mode, and it's working really successfully. There are a few centers that have copied the same module from us, and we have delineated this module in the paper itself. Of particular interest within the rare diseases group has been lysosomal storage disorders. For those that are not familiar, you usually have an enzyme deficiency which causes a storage of substrate within the body that leads to various clinical manifestations. There are many disorders that come under this, nearly 55 to 60 disorders, but Gaucher disease, which is worldwide the most common disorder, has been the area of interest for us. We have one of the largest cohorts anywhere of Gaucher disease, and all the molecular testing for this disorder has been developed within the center. So the baseline diagnosis has been easy for us. But what we are seeing is real rare phenotypes, which has not been easily described in the West. So the types that we see here is very different from the Caucasian or the Ashkenazi Jewish phenotypes, which are adult onset and milder diseases. What we see is under 2 years or 3 years of age, these children present with massive abdominal enlargement, and they have splenohepatomegaly with all the attendant hematological complications. And untreated, they die pretty much under 5 years of age. So detecting that there was a common mutation that was most frequent within the Indian and to some extent the Asian phenotypes, we started having to actually manage these conditions. And the gold standard for treatment is enzyme replacement therapy, where the body that is missing a particular enzyme to remove the substrate can be substituted intravenously on a fortnightly basis. So this is what we try to achieve. But as you can see, these are imported medications that come at great cost. For a 10-kilo child, today it costs about 40 lakhs per year. And there is no agency that will easily give you this kind of medication. With all the interventions that have happened so far, there are about 180 children only in the whole country that are on enzyme replacement therapy. At least a fourth of them are in our center. So we've worked really hard to see that we can get, and some of these patients have been on therapy for as long as 12, 13 years. My first generation of treatment savvy patients are now adults and planning college or planning to have children, getting married. And it's very satisfying to see that they're getting there, however expensive it is. And that was something that Dr. Kiran Majumdar also alluded to, that not only do we require therapies, we require cheaper therapies that become possible for other people elsewhere, and that we can reach out to the wider access. Now, this is the consequence of good therapy. So these are the early 5 to 7 year post this thing of the same Gaucher patients with those enlarged abdomens that you saw before. And these are some of the school, and so they consult us for everything, including what schools to join, which are the days that they can take off to come for enzyme replacement. And they have a fraternity between themselves. And so they also advise parents and children of their own age group about how to make it most efficacious when it has to be therapy related. And it's very gratifying to see them in all the social functions that we did. Now, all this would not have been possible had we not liaised very strongly with the parent support groups. We are fortunate that the largest of these umbrella groups, the Organization of Rare Diseases India, or ORDI, is based out of Bangalore. We also liaise with at least 25 other support groups. And on regular occasions, we go out to the public, we go at all sorts of levels to raise awareness, to raise a lot more than just awareness, to achieve early therapy wherever possible, wherever diagnosis can be done. And these events happen almost on a monthly basis. Now, In addition to that, it has been important to approach state government, and I have to say that this state government, Karnataka state government, has been very forward-thinking as far as where they've had real inputs into doing things that have been crucial for the therapy of these patients, and that is why we've grown forward in this exercise that we have gone through. So there was a time when we were struggling to get treatment for these patients, a collective of these patients, all of whom had been treated under Indira Gandhi and CHG combined, actually approached the state government, state judiciary, and went for the request for therapy. And they won this court case. And in 2016, the first installment of government funding came through for therapy, and this was a breakthrough because this was the first in the country. It has led to a lot of precedents since, and has also been the prelude to the national policy that came through as a result of this. Till today, we have received about 37 crores from the state government, and the numbers increase because, being a successful state, we get a lot of requests from all over the country to come and approach. Unfortunately, health is a state subject, so we are restricted by whom we can give therapies to. As soon as therapy started coming, and these are expensive therapies that cost 1 to 1.5 lakhs per vial, the whole issue became, where do you give them? In a general government hospital ward, how do you maintain the cold chain? How do you keep things going? And who takes charge of these medications that are coming through? Especially because you have to give feedback back to the government. So then, with private-public partnership, Indira Gandhi Institute of Child Health, Center for Human Genetics, and with a lot of other support, we started a specialized center of excellence for rare disease treatment in Indira Gandhi Hospital, which is the largest state children's hospital, and with whom we have an MOU since the last about 15 years. And this rare diseases ward has been responsible for treatment of patients in the daycare setting for a number of rare disorders, and has been the model for other states to copy right through. We have it next to the PICU in case there are complications. We have it away from infectious diseases, and it has been a real successful model. Today, we have at least 206 patients who come in regularly for therapy in these places that are beyond enzyme replacement, whether it's PIDs or whether it is growth hormone therapy or albuminemias. Or there are lots of conditions that come and get treated in these centers. We also found the need for the inborn metabolic errors which present in the first weeks of life. From 1965 onwards, most Western countries have a newborn screening program for a growing number of disorders. I think in the state of Texas, about 60 different disorders are tested for in the first week of life. We still don't have a widely available national program, and we are still prioritizing 2 disorders that are easily treatable but hasn't yet made it to a national government program. So therefore, these disorders don't get picked up early enough. The most common disorders are phenylketonuria and other organic acidemias that we see in our population, and many of these are amenable to be treated with specific diets that can be started early and prevent irreversible brain damage. When we started importing tins, a single 3-kilo child requires about 3 tins a month of a baby food-sized container. And a single container imported would cost between 16 and 20,000. We struggled a lot, but now with a local company, we have actually partnered to start making food products for at least 14 or 15 different disorders, and we've been successfully using this for the last 12 to 15 years. That was the first patient's graph on how the values of phenylalanine came down, and we have had since then recognition through the country. FSSAI has approved it, and it's available throughout the country. In fact, it also gets exported to neighboring countries. And we have had successful results. And when the children started growing up, we needed something to send them to school with. So we have developed atta, which you can make chapatis or dosas and biscuits, and now glycomacropeptide drink, which people can take to school with them, so that we can ensure that they're doing well. So many of our children are now doing well as a result of this, and the journey continues. For families that have these autosomal recessive disorders, and just looking back upon the cohort of our patients, nearly 70% of families come from closely consanguineous backgrounds. Most of them have recessive disorders, therefore there is a recurrence. It's not enough just to treat, but also to prevent future pregnancies from having that. This is a huge shortage within the country, but we have been lucky right from the beginning of having the Bangalore Fetal Medicine Center partnering with us. And we have done, I think, nearly 3,000 to 3,500 invasive prenatal diagnoses till date in families that we have diagnosed and then have gone on to have children. So it can either be done by invasive testing where you do amniocentesis or a CVS starting from 11 weeks onwards, or it can be done only by scans. So this is a child with golden heart syndrome where you have ear defects. And as you can see, it can be identified quite clearly as long as the scan machine is able to be run by somebody that is an expert that can detect the parts. Traditionally, ears are not looked at in anomaly scans, but it just shows you that by knowing what to expect, and because golden heart syndrome, which is shown over here, has completely normal intellect, you could advise the family that with a little bit of surgery, child should be fine, and we should be all right with most of the conditions, and the family opted to continue. So a lot of counseling starts antenatally. Now, all this requires manpower, and there's a critical shortage throughout the country of manpower that is clinically trained to translate these results onwards to families. And today, as we stand today, there are less than 120 clinical geneticists throughout the country. We set up in 2013 with RGHS a pediatric genetic program, which has been attracting doctors from all over the country. We have 12 doctors already trained and practicing in different places. We have 2 more in the current program. We also try to train. We don't have a formal counseling program, but our people who work with us through counseling actually have gone abroad and become successful counselors in some of the best universities. We are trying to get metabolic diet training for people who can be advised about diet. And of course, we teach on the MSc program on bioethics and human genetic counseling. So these things are growing as we go on. And with the numbers that are coming up, obviously comes, I think all the meticulous phenotyping we try to do has helped us publish quite widely. And in fact, just 2 days ago, we had our paper on a very rare skeletal dysplasia that has come through in Journal of Medical Genetics. But most of these are required because it all requires really detailed phenotyping if you're looking at rare syndromes. And to be accepted in some of the most significant journals has been very gratifying for all of us. More recently, to reach out to the actual community, DBT has started the UMEED program, which is for the unmet needs of inherited disorders. We've been shortlisted. We're hoping that the funding will come through. Sir's been on the committee, chairing the committee. And what we hope to do is actually with several other medical colleges and other institutes, to work together to reach out to the community as far as testing pregnant women and young children for the rarest of disorders where intervention can be possible. And lastly, in acknowledgement of all the work that has happened so far at the center and from the center, the rare disease policy for the country got announced in 2021 March in the midst of all the lockdowns. And we are one of the 8 centers that have been acknowledged as centers of excellence nationally for the work that we have done in rare diseases so far. And there's a representation on the Central Technical Committee, which is still making guidelines nationally about the types of patients that need to be treated and the priorities that need to be addressed. And all this that we have been doing is with a small little team under the guidance of 2 directors who have been very proactive in supporting my type of work, which, considering they're scientists, is really something that we are privileged to be with. And so we've got 3 other consultants with me, Dr. Kruti, Dr. Venu, Dr. Surya, 2 counselors, Monisha and Dhanashri, our PhD student who's working with hearing loss at the moment, and 2 senior nurses, Silji and Binsi. And with this small team, as you can see, represented with a lot of women, we managed to achieve what we have done. And we hope this can grow in the future. Thank you.
Thank you so much, ma'am, for the overview regarding the clinical activities that we do. I would now request all of you to have a cup of tea and a coffee and, energize yourself again for the next session. The tea and
giving an overview. In fact, I should say it's more like a bird's eye view of the research which is being conducted currently in our center. With the 20 minutes that have been allotted to me, I hope I can do some justice. Okay, and I'll have to start saying, I hope I'm going to represent the research that the faculty, in fact, have given me their slides. I hope I'm going to be able to cover most of it. But in case I cannot, and if you all have questions about this, the posters are out and you all can interact with students and get the information. So let me start with the research work of Professor Jairam. So you all have heard so much already with respect to diagnostics that's been carried out by Professor Jairam and his group. But with research is concerned, this is something really quite interesting. He's talked about these various chromosomal breakpoint mapping. And that's what I'm going to give one example. Now, with the DNA, the DNA duplication, chromosomal duplication, segregation, and everything, all these processes are so well and so dynamically regulated. One would think that nothing should go wrong. But in fact, you've seen already the number of chromosomal aberrations which have been reported and which have been associated with diseases. And as Professor Jairam has already introduced to you, the Philadelphia chromosome, where there is a translocation from chromosome 9 to 22. Now, at that time, when it was first reported, till now, there have been, science has come a long way, and there are so many other techniques which have been introduced, and which are being used by Professor Jairam's lab to map not only the breakpoint, but the genes involved in that breakpoint, the genes which get disrupted. And this is what is, so the mapping starts with a larger probe. I think he's already discussed these probes with you, which are, by the way, being made in his lab. So start with a larger probe that represents the entire segment that is transferred, but then there are shortening of these probes until it comes to something like 10 kilobase, and then find out the genes which have been disrupted because of this translocation. And the example that Dr. Jairam has given is the case study of a patient showing symptoms of insensitivity to pain, and as well as corneal opacity. Now, this person suffered from the hereditary sensory and autonomic neuropathies. So they found out that this patient showed a translocation between the chromosome 10 and 22. Now, to determine the genetic cause of pain insensitivity, they went on with the process that I just described, coming with truncated probes for in situ hybridization, and then ultimately were able to show that there's a disruption in the gene ENTPD, which is ectonucleoside triphosphate diphosphohydrolase. And this is in fact associated with, or deficiency of this gene product in fact is associated with several neurological symptoms. In this particular case, it was pain insensitivity. You all have already seen several of slides which Dr. Jairam has already showed, but for the presentation to be colorful, I had asked him for some slides, and this is the fish probes which are made in the lab. They're showing these are from amniocytes, which is prenatal diagnosis, and this fish probes shows on the right, this panel shows trisomy, which already has been. The fish probes, I thought this was also very beautiful, the 2 BCR and Abelson gene and the translocation therein, probes made by them. This is the normal female karyotype. Again, this is a repetition of what he said, but I'm quickly going through that. The abnormal female karyotype with the marker on the left, and in case of the abnormal male karyotype on the right, you can see the translocation between, in case of the male karyotype on the right, it's 2 and 7. So painting chromosome really helps. And this has definitely this technique, in fact, is able to not only show translocations, chromosomal rearrangement, also it's able to pinpoint the genetic abnormalities with respect to the enzymes that are involved and which bring about deficiencies. So the next lab that we can get into is Dr. Swati Shetty's. So the research focus of Swati Shetty is genetic factors associated with 5 different conditions, but the ones that I'm going to talk about is coronary artery disease. This is PCAD, that's premature coronary artery disease, as well as Noonan syndrome and Rastopathies. I'm going to introduce Rastopathies in a while. The others are glycogen storage disorders, Gaucher's, and genetics of infertility. So the genetic factors associated with the coronary artery disease in their study, Dr. Swati has included all the previously identified polymorphisms in the genome-wide associated syndromes studied in their cohort, as well as included some, for example, the SNPs, or single nuclear polymorphisms that may be involved in hypercoagulability, as well as systemic inflammation, both of which are associated with coronary artery diseases. So they have concluded that one of the most robust loci associated with this CAD has been the chromosome 9 and the P21 locus. Now, coming to Rastopathies. So the example here is Noonan syndrome. Now, the MAP kinase, which is driven, the signaling of MAP kinase driven by RAS. This pathway is the signaling or the center of several signaling pathways in several cells, several ligand receptor interactions. Now, therefore, it's not surprising that any anomalies or any deficiency, any mutations in any of the components of this pathway would lead to some kind of condition. And now there are 107 Noonan syndrome affected individuals that have been typed here, and the number, as you can see, the number of mutations which have been shown along the entire exon here of the gene for phosphotyrosine phosphatase, so not kinase, but phosphatase, which is associated. And going further, doing the NGS on the same, there are 22 genes which have been shown to be involved in this Rastopathies. Now, why Rastopathies is because I just mentioned that the RAS kinase family, which in the signaling involved in RAS as well as MAP kinase. So Rastopathies is all the abnormalities or deficiencies which cause disruption of this signaling caused by RAS mutations, and therefore Rastopathies. So there are now changes in 50 patients, and this is the diagram that shows the number of mutations that they have reported and involved in Rastopathies. Now coming to the next laboratory of Dr. Pratibha Ranganathan, who is a cancer biologist. And the research focus of her lab presently is understanding the molecular mechanisms that underlie resistance, chemo resistance. Now, chemo resistance, I'm sure this is something that most of you all do understand. In spite of the growing data and reports on cancer research, chemotherapy as well as radiotherapy are still, and these are, of course, conventional therapies that are still in place in most cancer hospitals. Of course, they're very efficient, but there's always a residual disease that happens, and these tumors that are in the residual disease, once they get the opportune moment, they come up and start to again cause metastasis or secondary disease. Tumors, the residual tumors, in fact, become also highly resistant to chemotherapy. They evolve this themselves. And what is it that leads to this resistance? If one can find out what are the molecular mechanisms, then it would not be difficult to be able to identify and come up with strategies, but keeping these in mind. And this is the focus of Dr. Pratibha's research. Now, they are looking at both intrinsic as well as extrinsic factors. Now, intrinsic factors are what the tumors themselves have evolved to come up with this mechanism to become chemoresistant. And extrinsic factors are now something that all cancer biologists have started to look at. It's not only the tumor, but tumor tissue per se, but also the microenvironment, such as fibroblasts, which contribute to this disease condition. So taking both of these, in both intrinsic and extrinsic factors, now encompass the approach by, at the bench first, starting with cell lines, making cell lines resistant by constant exposure to sublethal doses of reagents or chemotherapeutic agents. Then looking at the expression profiles, if there is any difference in the genetic, the gene expression profiles before and after the cells become resistant to chemotherapeutics, and also taking a cue from the bioinformatics. There's a lot of data mining that needs to be done because there's a lot of literature that is available now to say what could be the different areas, which are the genes, which are the mechanisms which go to give this resistance. So based on all these now, they have come up with trying to identify those genes. I'm not going to talk about that, will be on posters, which could have some relevance with respect to developing chemoresistance. One thing that I wanted to also mention, that Pratibha's lab is also not only doing, I think some of you probably already know, that 2D cultures is what we all have been, my time, we were doing only 2D cultures. And it was found that for any kind of a study using 2D cultures, it's futile unless you have a sphere, a sphere of cells which would mimic what happens in the tumor, in vivo. So Pratibha's lab has also been able to do that. Using now transcriptome analysis, using messenger RNA as well as microRNA analysis of these resistant cells, they should be able to come up with a profile of mechanisms that govern the cells to become resistant to chemotherapeutics. So this is the tumor microenvironment interaction. These are cancer-associated fibroblasts, which seem to provide soluble factors which allow these cancer cells to, in fact, grow better. So one shouldn't be taking care of only the tumor cells and looking at the intrinsic factors, but also the ones that come from the fibroblast, which is in the microenvironment. The next lab I would like to talk about is Dr. Ravi Hiremeglur. He's a clinician, and he is so his idea is to look at skin anomalies, so everything to do with genetics in skin anomalies. And the example here, which is the slides, the next slides, in fact, not very nice to see. This is a condition called epidermolysis bullosa, and this is genetically associated dermatosis characterized by spontaneous or trauma-induced blistering on the skin and mucosa. There are about 20 different genes which are associated, which have been identified relevant to this condition. And this is also clinically genetically heterogeneous. So the work strategy Dr. Ravi has adopted is, first of all, seek referrals through online link, then also have multidisciplinary clinics, also do skin biopsies, because there's 20 different genes involved, so do skin biopsies, and map the proteins in the skin biopsy using immunofluorescence, using monoclonal antibodies. Now for that, he has teamed up with Dr. Gurudatta Barka, and who has made a panel of these antibodies, and I'm going to show a couple of them later. Of course, finally, the whole exome sequencing, followed by Sanger's validation, would be something that needs to be achieved at the end of this program, or during the program after a good number of samples have already been tested. The observations from Dr. Ravi's lab, there are already 220 patients that were enrolled, of which about 160 are already registered. And 134 samples of these patients have been sent for clinical exome sequencing, and 105 already have been, the data has been obtained and ready for analysis. And 5 families were successfully directed for prenatal diagnosis. So that's, I think, a very good step forward in this direction. These are the publications from his lab, and this is his team, and I don't have time to go over all the names. So I'd now like to come to Dr. Sudha Srinivasan's lab, whose interest has been studying mutations associated with MPS. Dr. Meenakshi Bhatt has already dealt with this mucopolysaccharidosis, which is in fact again a multifactorial disease. This is a disease of the lysosomal disorder, and you all know that lysosomes have so many different proteases, and deficiency in any of the proteases, some of them actually are, give very severe symptoms, and some can be managed. But deficiencies of any of these can cause conditions. In this case would be deposition of, if it's lipids or carbohydrates in monocytes, and which get deposited in liver and other organs, usually lethal in childhood if not treated. And the second one is diabetic retinopathy. So with respect to MPS, so the idea is that if one can identify mutations in this, it might help to understand the pathogenesis of this disorder. And so the lab has chosen MPS 6 mutations, and these are the different mutations that have been identified in the laboratory. Of course, the study is still ongoing, and one needs to have a good number to be able to come to those that are prominent, the mutations. Indians are genetically predisposed to diabetes type 2. I think this is again something everybody knows. And it's only, so there are a very large number that are stricken with this condition, but it's only a small number that come down with diabetic retinopathy. So the question that Sudha asks is, what are the mutations in these diabetic individuals which make them susceptible to the cause of vision impairment, that is retinopathy? So she has gone on to study single nucleotide polymorphism in the VEGF, vascular endothelial growth factor, A gene, which is what the subject of study has been whenever there's anything to do with any study with respect to circulation. So study groups, they have taken cases of diabetic retinopathy, individuals who have, of course, had associated, first had diabetes, and those which do not have retinopathy would be the controls. So they aim to have about 300 patients in each group, and they have started to look at the specific SNPs in the VEGF-A gene. These are the different SNPs being studied presently, and they've completed analysis of about 100 patients. Their target is 300 before they can come out with the conclusion and results of this study. Now I come to Gurudatta Barka's laboratory. When I asked Gurudatta to give me his slides, he gave me 5. He told me, I'm giving you 5 slides, but you should look at the data on the 5 slides. But now this is an institute for human genetics. So most of the labs, of course, are looking at diseases and conditions with genetics in mind. So the first 3 that you can read here, the first 3 programs are related to genetics. Regulation and function of chromosomal architectural protein in neurological disorder, epigenetic and chromatin mechanisms in fragile X-associated tremor and ataxia syndrome, and studies on the genetic variability of human ACE2 receptor gene and the expression status along with prevailing. Now, the last 2, yes, I'll come to that, development of ELISA, but this is the first one, and I'm sure all of you would have questions, and I saw posters depicting this, so please ask the students. So this is regulation and function of chromosome, the first one, the CTCF. This is with regards to the fragile X tremor ataxia syndrome, and this one is the ACE2 receptor. Now, just like to mention this, that Guru Datta is Drosophila geneticist to begin with, and therefore all these disease models, for all these diseases, he used fruit fly as the model. So he has several publications in this line, and I think you all can discuss with him. There's too much on the slide for me to have. I didn't know what to delete and what to keep before I presented, so I said, let everything be here. Now this ACE2 receptor. Now ACE2 receptor is something to do with corona infection. Now again, all of you all do know that some individuals, even in a given lab, let's say, not everyone came down with ACE2 infection, and even those that came down with the corona infection, sorry, not ACE2, corona infection, did not, there was variability of the severity of the symptoms. Now this, of course, was because of the immunological system, but the transmissibility dependent a lot on the ACE2 receptor. And so Guru Datta decided to look at, and this is a project that he's just started along with Bangalore Medical College. What is it? Is there any genetic susceptibility with respect to transmissibility of the coronavirus? This is what he's going to look at, and this is really quite interesting and very relevant in the current scenario. Guru Datta's lab has also developed a Corona ELISA, COV2 ELISA for serosurveillance. It's very nice. And this is what I was talking about. He's collaborated with Dr. Ravi in making monoclonal antibodies, and he's planning to make a panel of them which can be used to now diagnose conditions with conditions of skin disorder. So this is anti-human keratin 14, anti-human laminin beta, and anti-human collagen, and been quite successful in getting specificity in immunofluorescence. Now, last but not the least, this is another fly lab, Dr. Carmen Coelho's. Now, this is something that I must say I don't understand much about. So I'm just going to say exactly what she has written. So she uses Drosophila to study fundamental aspects of size determination. This is something quite interesting. And to model human genetic disorders, therefore, that affect growth. So this would be, again, similar to what Guru Datta is doing. This is a fly model that one can now use to determine genetic disorders. So what was interesting is coming up. So Carmen is quite the novelty here with respect to now doing a mathematical calculation with respect to the rate-dependent synthesis. Now she's exploring the possibility that size does not feed back onto growth rate during development, but instead growth rate is regulated by rate-dependent negative feedback. This looks very interesting, and please do discuss this with her. And there are a whole lot of graphs which depict the same thing. And yes, so she comes with the okay, this is with respect to the disease that she would like to look at. This is the human disease. This is due to somatic mutations that increase activity of the PI3 kinase AKT pathway. Again, for students, you all would have studied this in your cell signaling class, so you all know what is the AKT pathway. And Carmen has also got a grant to look at this abnormality. So I do hope that I finished this in 20 minutes. I went like a mail train. And if there are any questions, please ask the faculty when they are standing next to their posters. So this was a bird view of the research that is going on, but I'm sure you all know, you all can see that though genetics is the central point, everybody is using so many different methods and mechanisms and technologies to answer questions with respect to disease biology. So thank you.
Thank you, Professor Anjali. It's well said that eminent breakthroughs in science comes with research, and I think Professor Anjali has covered it well. We now carry on forward with talks for the day, different scientific speakers who are with us today. I invite one of our faculty, Dr. Swati Shetty, to introduce the first speaker. Thank you.
Good afternoon, everyone, and it's my pleasure today to introduce Dr. Deepak Modi, who will be our first speaker. And as you will see, he's someone who has achieved a lot in a very short duration of time. He received his PhD in 2003 from University of Mumbai in human genetics, and joined the NIRRCH, which is the National Institute for Research in Reproductive and Child Health, as soon as he finished. And presently he heads the molecular and cellular biology group there. And to touch on a few of his achievements, he was the recipient of the INSA Young Scientist Medal in 2006, the National Academy of Science India's Platinum Jubilee Young Scientist Award, and the Innovative Young Biotechnologist Award in 2007. He received the ICMR Tilak Venkoba Rao Award in 2010, the GP Talwar Young and Middle Career Scientist Award by IISSRF in 2009 and in 2017. He has also received the PM Bhargava Oration Award in 2017, and in 2020, he was elected as a Fellow of the National Academy of Sciences in India. He has over 125 publications to his credit, and currently his research areas include the understanding of endometrial receptivity and endometrial disorders, genetics of sexual development and male infertility, and COVID-19 in relation to reproduction. He's also currently the co-investigator of the PREG COVID registry, which collects information on pregnant women with COVID and their babies. So thank you for agreeing to speak today at our Foundation Day, and I request Dr. Deepak to please.
Thank you so much for inviting me. A special thanks to Dr. Meenakshi and the Director Jaidam for having me here, and I'm really overwhelmed for being here, and I'm nervous also seeing the audience because, overwhelmed because this institute started when I joined for my PhD in human genetics, and I relived my entire PhD when Sir presented all about fish and chromosomes and making their own probes, and I realized all the ordeal and the trauma that I went through while doing the same. And then I see Dr. Dipti Devbakar, who was my thesis referee, and Dr. Sharat Chandra, who I've been always admiring since my PhD days. We had never an opportunity to meet, but I'm so glad to be here. And Dr. Anjali Kharande, who has been collaborator to my first PhD student thesis work. So it's been a very overwhelming thing, and I'm really very nervous giving a talk, but let me try to settle myself. And that's just to give my quick overview of my lab activities. I already said that my lab is interested in understanding fundamental mechanisms involved in initiation of pregnancy. So I drifted off from clinical genetics, and when I got into NIRRH, I got into understanding how pregnancy is initiated, how the placenta is formed, and how things can go wrong in these processes to cause infertility or recurrent implantation failures, or even pregnancy-related disorders like preterm births. And of course, carrying on from my PhD work, genetics of sexual development and sex determination has been very close to my heart, and as a side project in the lab, we continue to do that work. And we're also looking at genetics of male infertility, mainly Y chromosome microdeletion, which from a very basic research aspect has now got into a translational aspect, where we have developed a kit for diagnosing Y chromosome microdeletions for the Indian population. I'd like to talk about it at some point later. But for today's talk, I'll be talking one of the side projects happening in the lab of understanding the genetic mechanisms of sex determination. And for that, I gratefully acknowledge my graduate student, Neha, who has worked very, very hard to generate all the data that I'll be showing today. And she was teamed up with Domdat and Anshul, who have helped her in doing a lot of this work. And I just present their work to you here. And we team up with Dr. Mohit Jolly from IIC Bangalore and his wonderful graduate student Sarthak, who have more recently got into the team, and we are looking at it in a slightly different way than we have been conventionally studying sex determination. So why study sex determination? We are all sexually dimorphic species, and we identify ourselves as a man and a woman. We live in a gender binary society, and what gives this gender identity to each one of us is of fundamental importance, because when these identities go wrong, we can have a lot of socio-psychological trauma, because we believe that man and woman are the only two parts of the spectrum and there can be nothing in between, which is not true. And statistics have shown that nearly 10% of individuals have some forms of gender identification differences, and what causes them is a larger question that we want to ask. But one of the things that gives us gender identity are our gonads. They produce the right kind of hormones, they produce the right kind of things, which then prime the rest of all of our tissues to give the sexual identity. And one of the most important things in that process is the germ cells, which gives us the ovary, which in the ovary gives the ova, and in the testis gives the sperm. And what allows these germ cells to be the way they are is a fundamental question which we are asking. And irrespective of whatever we identify ourselves with here today, everyone sitting in this room, everyone across the globe, in our mother's wombs at some point we were bipotential. That means when the gonads were developing, they never developed as a testis or an ovary, but they developed as a bipotential structure, which then at some point took a decision to either go into the male pathway or the female pathway. And the factors which allow these gonads to go into either of the pathway allow us to explore what are the factors involved in genetic switching, how the genetic switches occur between the two sexually dimorphic species. So we try to understand this question. And just to give you a very brief overview about it, it's a very complex subject, but what we all know is that in the developing gonads, there are supporting cells, there are steroidogenic precursors, and there are germ cells. And at some point, both of these have the ability to go either in one of the directions. It is currently understood that the supporting cells first take a decision. In the mammals, the SRY gene gets activated. In other species, it's SOX9, which allows the supporting cells to either go into the Sertoli cell lineage or it can go into the granulosa cell lineage. At the same time, the steroidogenic precursors can go into the fetal Leydig cell lineage to produce the hormones, or it can go to theca cell lineage, which later on in life will produce the hormones. And the germ cells have to either go into the spermatogonial lineage or the oogonial lineage. And my talk will be focused only on this aspect for today. So just a brief overview. The germ cells don't develop in the gonads directly, but they develop somewhere outside the embryo. Probably near the yolk sac. Some of the germ cells specify. Professor Azim Surani has done wonderful work of how these germ cells are specified, and then they migrate through the hindgut and they get into the gonad, and in the gonad eventually they get into the male lineage or the female lineage. One of the determining or the sexual dimorphic factors of these germ cells during development is the entry of germ cells in meiosis. In the XX gonads, or the somatic cells which have taken a decision to become the female, the germ cells at the same point enter into meiosis. Alternately, if the supporting lineage is that of a male, then the germ cells enter into the spermatogonial lineage. So this is where the sexual dimorphism or the decision-making process occurs. So entry of germ cells into meiosis is during development is the determinant of sexually dimorphic fate in the developing gonads. In the testis, the germ cell enter into meiosis much later during adulthood, whereas in the fetal ovaries, the germ cells enter in meiosis, they remain suspended in meiosis for a very long time, and then carry on oogenesis in adulthood. So the germ cells are pluripotent in nature. They are stem cell while they're developing when they enter into the gonad. And these pluripotent germ cells have to exit from meiosis, exit from pluripotency, and either get into the meiotic prophase program, or in the XY gonad, it has to undergo mitotic arrest. And what we know is that in the XX gonads, they first acquire a gametogenic fate, and then they activate these two genes called as RECATE and STRIATE, which allows them to enter into meiosis, and the premeiotic DNA replication and the meiotic process is initiated. This entire process is inhibited in the XY gonad, very nicely inhibited in the XY gonad, so that they don't enter the meiotic phase, and they go into the Nenastu pathway and then undergo the male fate into the mitotic arrest. So the question that we were asking was that since this is a nice system to tell us how the cell fate decisions can happen, we asked what are the master regulators or what are the genetic networks operating during this time which allows these germ cells to take either the meiotic lineage or into the mitotic lineage or a mitotic arrest lineage. And today we'll be focusing mainly on this aspect because that's what we have landed up discovering in the last 8 or 10 years or so. So please, for the students, whatever I'm going to talk in the next 20 minutes is not 2-3 years work. It's a work of 10 years. Last when I gave a talk in CDRI, and after I reached Mumbai, I got an email from a student saying that I loved your talk, it was wonderful, can I come for a 6-month internship to have a paper from your lab? And I'm like, things don't occur this way. This is like a real long way, and some experiments have taken 2 or 3 years to get us to that point. So please, students here, just get your nerves thing. It's not a 20-minute magic that just comes out in some time. So anyways, in terms of timeline, the project doesn't go, what my presentation will not go according to the timeline that the project was going. We had a lot of bits and pieces data, and today I'm presenting it like a story. So because of our interest was to understand genetic networks which are involved in gonad determination, mainly sex determination in the germ cells, we thought let's use single cell RNA-seq data. So the good part for us is we didn't have to do these experiments ourselves. Most of the data sets were already uploaded by others, and we took 2 data sets from the mouse. One is whole gonad XX gonad 11.5 to 14.5. I'm sorry, I missed one point. I should take you there. So the timeline for sex determination is very well defined in the mouse and also in the humans. At embryonic day 10.5 to 11.5, that is when we make the animals, the day of vaginal plug is considered as day 0.5, and 10 days after that or 12 days after that. If we dissect out the gonads, at 10.5, 11.5, the germ cells are still in the pluripotent stage, but at 12.5, the germ cells starting to take a decision to enter into meiosis. By 13.5, they've entered into meiotic prophase, and by 14.5, they've acquired a oogonia phase. So these are the timelines which we thought let's have a look of what is happening to the germ cell transcriptome. So we took published single-cell RNA-seq data set. So this is done by Mohit at ISC. And we had a whole about more than 4,000, 5,000 cells, ovarian cells at 11.5, 12, 13, and 14. We thought this is a nice window to look at changes in transcriptomes. We had another data sets where this was total ovarian, total gonad cells, whereas this was cells, only the germ cells isolated from the XX and XY gonads. And then single cells were analyzed for the transcriptome. And we thought these would be nice 2 complementary approaches to understand what is happening to the changes in transcriptome during the acquisition of the sexual fate. So first things first, we wanted to ensure that our tools are right, the pipelines developed by Mohit's lab were right. So yes, we could cluster all the cells. We can see that they're different. There were about 17 clusters which we could get of the cell types that we were looking at. And of them, you can see here marked are the germ cell clusters. These are germ cells because it expresses gene called as DDX4, and DAS-like, which are the germ cell specifying markers. This is the other data set where they've compared XX and XY, and yes, we have a whole lot of germ cells very nicely classified. The XX and XY germ cells behave in a very distinct fashion. So we were happy that yes, our transcriptome data are there with us. The pipelines are going good, and now we thought let's start exploring what's happening in them. So it was getting very complex because this is a timescale analysis, and we only wanted to look at very specific timelines. So what Sarthak did was, he first put this in simple PCA plots across a pseudo time, and he could define these germ cells into 2 distinct clusters. They went in a V-shaped profile, and we could see that these germ cells have a very distinct gene expression profile versus those here. And when we look at specific markers, all these germ cells on the left side in pseudotime are labeled with the mitotic markers. So this means these were pre-meiotic or the early germ cells. And later on, the other cluster which we could well define here. So this I said is a mitotic population, and this population is a meiotic population. So we were glad that our data sets were getting into 2 different clusters, and now this allowed us to probe what is happening in there. So the first thing we did was we looked at this mitotic cluster, and we looked at the classical pluripotency genes. And here is nanog. I'm sorry, the writing is a little less here. But nanog was expressed at very, very early stages, and its expression started switching off as the germ cells were wanting to enter meiosis. SOX2 was expressed along with NANOG, but it was also expressed in later time point. And to our surprise, OCT4 was coming, which was very low early, started coming up a little later when the germ cells were wanting to enter into meiosis. So we thought, okay, the germ cells just don't switch their fate one fine morning, deciding that, okay, now we are in mitosis, let's run into meiosis. It's probably occurring like a defined program of switching off of pluripotency and switching on of something which is letting them enter into meiosis. So then we probe further and we realize that there is something called as a transition cluster. In this cluster, the genes, the cells were co-expressing some of the pluripotency markers and the mitotic markers, but some of the markers of early meiosis. So we first put up all the early meiotic markers, known meiotic markers in literature, and these cells were labeled very nicely there, and the cells here were labeling the late meiotic markers. So we thought, okay, this is not the nice population for us to look at. We wanted to look at this particular population, and two classical genes, as I said, RECATE and striate, are well known for their entry into meiosis. So we found that RECATE is somewhere here, which is covering our transition zone. Striate was also there, but striate was also expressed in the late meiotic cells. So we thought, okay, striate might not be a very nice marker to explore what is happening at the time when the germ cells want to switch their fate. So what Mohit did was he looked at RECATE co-regulated genes, genes which are switching on and off along with RECATE. And he found a large numbers of genes. The strategy was nice because at least 3 of the genes in this cluster were known to have roles in meiosis. So we thought the strategy is good. And now we had a whole lot of genes which were possibly involved in either switching off of pluripotency or switching on of entry into meiosis. One of the genes that caught our attention was this transcription factor called as LHX2. LHX2 was almost expressed in parallel with RECATE. In fact, it was also expressed a little earlier than RECATE in this transition cluster. It only came up in the transition cluster, and as the cells went later into meiosis, this expression switched off. So now we have this gene which is switching on for a very short time when the germ cells have to enter into meiosis and then going away. We thought this would be an interesting gene to look at. What Mohit also did was he looked at LHX2 and RECATE co-regulated genes and to see if there are any commonalities. And yes, we found a large numbers of genes which were common between the two. So we thought that yes, LHX2 has something got to do with germ cell entry into meiosis. And we thought let's explore that further. So what is LHX2? As I said, it's a transcription factor. It has a well-known role in brain development. It belongs to the limb homeobox gene family. Shubha Tole at TIFR has been looking at LHX2 or its context in development of the hippocampus and so on and so forth. And these LHX2 mice, knockout mice, which we got from Shubha's lab, they die around E15.5 to 17.5. We thought, okay, that's the timeline when entry into meiosis happens. So they are nice models for us to look at. But the good part for us was roles of LHX2 in the gonads were completely unknown. Nobody had ever reported that even LHX2 is expressed in the gonad before this. So we thought, okay, let's look at LHX2. But rather than looking at LHX2 in isolation, we thought first let's look at all sorts of limb homeobox genes, whether they're even expressed in the gonad. So this is a heat map, again from a published data set of the mouse, rat, and the human. And the ones which are lighting up in red would be female dominant, that is they're overexpressed in females. And the ones in blue are male dominant, that they're overexpressed in males. Because you're looking at sexually dimorphic genes, because the ones which would be required for female development must go high in females, and what is required for male development must go high in males. And we found that a whole bunch of LHX genes were differentially expressed, and several of them across species were either female dominant or male dominant. Of them, our favorite gene, LHX2, was female dominant in the mouse, rat, and the human. This excited us. We said, okay, now we are not looking at something which is just only in the rats, but only in the mouse, but also in the rats and the humans. And then this was followed by, of course, a standard way of looking at RT-PCR, LHX9, which was used as a control, not sexually dimorphic at 12.5, 13.5. LHX2, 12.5, a little higher in the female as compared to male. By 13.5, there's a robust induction of LHX2 in the female gonads, but not in the male gonads. So far, so good. Everything fell in place. What Domdat did was something more interesting. Because sex determination in mammals is genetically determined, that means you require the SRY gene and the SOX9 genes to get the male fate, and if you don't have the SRY and the SOX9 gene, you get into the female fate. But in turtles, this is determined by temperature. Some temperatures allow male development, some temperatures allow female development. What he found was that, so this was again published data sets. So the nice part here is that we didn't have to do many experiments ourselves. We just had to take the data sets and do a lot of secondary analysis. And in the turtles, the turtle eggs incubated at male determining temperature, shown in blue, or the female determining temperature, shown in pink. And the ones which are incubated at male determining temperature, in the female determining temperature, had higher abundance of LHX2 as compared to the male determining temperature. So irrespective of the mechanisms of sex determination, we always found LHX2 was higher. Lizard, it uses ZZZW as well as temperature, and whenever there was female development, higher LHX2 as compared to the males. Chicken doesn't depend on temperature, it uses on ZZZW, and again, higher in the females as compared to males. Opossum is interesting because it has extrauterine development. It doesn't develop in utero. And even in this species, LHX2 was always higher in the XX gonads as compared to XY gonads. Mouse and human have already shown you. So now here is a transcription factor which is expressed in the germ cells, which is expressed in the developing gonads at the time of sex determination. And irrespective of the species or the mechanisms of sex determination, it is always higher in the female gonads. So we said, okay, that's great. Now we were getting a little more greedier, and we wanted to figure out if LHX2 is only expressed by the germ cell. Somehow we had this fascination that if it is expressed by the other cells, we may not want to like it. But then our single-cell RNA-seq showed us that LHX2 is expressed only in the germ cell fraction, but not in the somatic fraction. And then we also did experiments to prove that, where we took germ cells from OCT4 GFP mice. These are mice which express GFP only under the OCT4 promoter, and we could IceFACS sort these germ cells. So the OCT4 plus fraction is a germ cell fraction, OCT4 minus is a somatic cell fraction, and we found LHX2 only in the germ cell fraction, but not in the somatic cell fraction. And as a complementary approach, we also took mice which are knockout for c-KIT. In these, the germ cells develop correctly, but they don't enter into gonad, and when they don't enter into the gonad, there is no c-KIT expression and there is no LHX2 expression. So we were like, kind of great, okay, now here is a system, here is a gene which is sexually dimorphic, expressed only when the germ cells are entering into meiosis or exiting from pluripotency, and it is evolutionary conserved, and it is only in the germ cells. Great, so now it was time to look at the knockouts. What does LHX2 do in the developing gonads? Does it allow the germ cells enter into meiosis or exit from pluripotency? So we did RNA-seq, bulk RNA-seq. This is one of the most painful and the longest running experiment ever, because these are like pinhead-sized gonads. There is mesonephros below which had to be removed, and then so many gonads had to be pulled up. Then we had to decide for the sex. We had to decide for the genotype. We had standard knockout mice. We had conditional knockout mice. So the entire team went crazy, and I think they must have cursed me several times during the entire experiment, because I was like, oh, I'm not convinced with this extra little thing coming up. Do again. And several pools were made, and after that, finally, we had so many differentially expressed genes. So all this 2 years' work just goes off in half a slide here. Anyways, this was then we went ahead the standard way of looking at genes and enrichment. I'm only showing you the data of E12.5 because other data points are more complex. These are the genes which are upregulated in absence of LHX2. And there were several processes which were involved there. And one of the processes that caught our attention was angiogenesis. This work is published. I'm not going to talk much about that. Generally, in the developing gonads, the testis has to undergo angiogenesis. Angiogenesis has to be suppressed in the ovary. But in absence of LHX2, what we have shown very recently is that in absence of LHX2, the female gonad starts developing like a male gonad. It starts doing angiogenesis, which otherwise it's not supposed to do. So there is something going wrong with the sex determination pathway itself. You can read this paper and get more details after. I'm not going to bother you about with that because germ cells is of our interest. So now imagine now there's something in the germ cells which is allowing other cells to misbehave. So this is something completely different, not anticipated, and we are working on that further. But our repress process gave us very interesting data. We got most of the processes involved in meiosis. So in absence of LHX2, processes involved in synaptonemal organization, meiotic cell cycle, female gamete generation, chromosome segregation, DNA repair were all downregulated in absence of LHX2. So we thought that is LHX2 required for entry of germ cells into meiosis? So what Domda did was he took all these differentially expressed genes. From that he sorted out only those genes which are known to be expressed in the germ cell. So these 524 genes are the genes which are exclusively expressed by the germ cell. So we call them as germ cell enriched genes. And we found that about 30% of them were differentially expressed and about 25% were only downregulated. Of these 524 genes, 104 genes are known to have roles in meiosis. And we found that out of these 104, nearly 40% of the genes were downregulated, indicating that yes, in absence of LHX2, there should be inhibition of meiosis. So, standard way, qPCRs. We did qPCR for Recate, DMC1, and SPO11, which are the early markers which are required for breakage of chromosomes. And we found that our Recate, DMC1, and SPO11 were significantly downregulated in absence of LHX2 at E13.5. Then I was a little wishy-washy here, and I said that, no, what if it is just a delayed meiosis? It may not be actually inhibition of meiosis, but it might be just a day delayed. So what Neha did was she took gonads at E15.5. By this time, all these genes should have caught up if there was a delay in meiosis. But again, at E15.5, Recate was down, SPO11 was down, although DMC1 had a little bit of catch-up. But that was not sufficient because these were just the entry markers involved in DNA breakage. What is very crucial is look at CYP1, CYP2, and CYP3, which are proteins which label the chromatin. And CYP1 was not significantly different, but CYP2 and CYP3 were significantly downregulated in absence of LHX2, telling us that loss of LHX2 does not allow the germ cells to enter into meiosis. I love this because I don't like qPCRs because you just see some numbers coming up. I'm a more visual person, so we did immunofluorescence, and here is DTX4, which is labeling the germ cells, and the yellow is a CYP3, and we find that in controls, almost every germ cell in the gonad is labeled with CYP3 positivity. But in absence of LHX2, this is the gonad. You can see the germ cells are there, but most of the germ cells did not have any CYP3, indicating that they never got into the phase of meiosis. But there were a few residual germ cells which did light up CYP3, telling us that yes, there are some germ cells which can enter into meiosis even in absence of CYP3. So what my intern Abhishek did was he counted at what stage are these CYP3 positive germ cells in the developing gonads. And what he found was, so looking at CYP3 expression pattern, that how they're loaded onto the chromosomes, we can segregate them into different stages of meiosis, that is leptotene, pre-leptotene, leptotene, zygotene, and pachytene. And what we find that at E14.5 in the controls, most of the germ cells are either in the pre-leptotene, leptotene, or zygotene stages. Some of them have already got into the pachytene stage. But in the LHX2 knockouts, less than 10% of germ cells were CYP3 positive, and these were only in the pre-leptotene, leptotene stage. Moving a day later, when in the controls, where most of the germ cells have reached the pachytene, zygotene, or the pachytene stage, these germ cells are still arrested in the pre-leptotene, leptotene stage, telling us that a bulk of the germ cells would refuse to enter meiosis in absence of LHX2. Some which kind of push themselves and get into it, get stuck at a very early stage, they don't progress any further. Now that we had got some expression of CYP1, I was getting a little more notorious, and I said that you're getting CYP1, that means meiosis should be happening at least in a subset of germ cells. CYP3 alone was not good enough for me. And what we know is that the chromatin which labels CYP3 has to acquire CYP1 to now start doing the crossover. So we started looking at CYP1 and CYP3. So normally these two have to overlay with each other. And in the controls, we find that in most of the germ cells, there was overlay of, so these are paraffin sections, very difficult to do anyways, but most of the germ cells did have CYP1 and CYP3 overlay. But in absence of LHX2, either the germ cells were positive for CYP1 or CYP3, barely any cells showed an overlay, telling us that even if the germ cells which are wanting to enter meiosis, they are chaotic, they are lost, they don't know what to upregulate, what to downregulate, telling us that now, yes, in absence of LHX2, there is failure of germ cells to enter into meiosis. Even if they enter, they get into a very chaotic stage and they cannot progress further and they just get arrested there. Now the question was how this is happening, that we had shown that loss of LHX2 halts the germ cells to get into meiosis, how this process is happening. So we thought that probably the germ cell numbers itself may not be sufficient. There might be some defect much earlier in entry. So we looked at these stages where we looked at this gene expression of MVH, which is a marker for primordial germ cells, and the DAS-like, which is essential for the germ cell to enter into gametogenic fate. And if the germ cells which are knockout for DASL never enter into gametogenesis, and since our germ cells were not entering into gametogenesis, we thought maybe MVH or DASL might be faulty. So looking at MVH, which is a marker for germ cells, both by immunofluorescence and qPCR, we did not find any difference in expression of MVH, telling us that the germ cells were correctly differentiated, the primordial germ cells correctly migrated, and the numbers did not change while they were in the gonad at the time of sex determination. We thought, okay, once these germ cells might not have acquired a gametogenic fate, so we looked at DAS-like, but DAS-like was also equally expressed at RT-PCR as well as at immunofluorescence level. Almost every germ cell which was positive for DDX4, which is MVH, was also positive for DAS-like, telling us that they had correctly acquired the gametogenic fate. So it was downstream to the gametogenic fate that LHX2 was required. And indeed, in the RNA-seq datasets of DAS-like wild type and DAS-like knockout, in the DAS-like knockout, we did not get any activation of LHX2, telling that for activation of LHX2 in the germ cells, you had to get them into the gametogenic fate. Now that it was there, we realized that everything here is okay, but everything here is not okay. So we realized that LHX2 should be somewhere between DAS-like and the Recate stage. And this is where the dissections now started, and we are still at an incomplete story here, but we are excited by it because we think that we have identified one of the earliest markers of transitioning into meiosis. What we know from literature is that the primordial germ cells get influenced by two of the molecules. One is BMP4, another one is retinoic acid. And this retinoic acid activates striate, allowing the germ cells to get into the gametogenic program and suppression of the prospermatogonia program. And later on, the same striate, retinoic acid and striate allows prospermatogonia in adulthood. So we thought whether the retinoic acid program is defective in these gonads, therefore these gonads cannot enter into meiosis. Now this retinoic acid program in the developing gonads, retinoic acid is produced by the underlying mesonephros and it just diffuses into the gonads irrespective of the sex. But in the male gonad, the Sertoli cells produce this enzyme called the CYP26B1, which degrades the retinoic acid, not allowing the germ cells to see retinoic acid, and therefore they would not enter into meiosis. Because CYP26B1 is absent in the developing fetal ovaries, the retinoic acid is not degraded, allowing striate activation. So we asked whether the retinoic acid biosynthesis and the retinoic acid degradation machinery were altered, or the receptors were going haywire. So this is from our RNA-seq bulk data, and the retinoic acid biosynthesis enzymes, their receptors were not differentially expressed, telling that the receptors were rightly expressed. That means the germ cells were capable of seeing retinoic acid. The retinoic acid was not degraded because CYP26B1 levels were not elevated, telling that yes, they can see retinoic acid and retinoic acid is there in the gonads. Then we thought that the germ cells still experience retinoic acid, and one of the ways of looking at it is looking at expression of striate, because it's the first gene that is known to be activated upon treatment of germ cells with retinoic acid. And we found that striate was significantly downregulated in absence of LHX2. That means the sensitivity of the gonads to experience retinoic acid is dependent on LHX2. What we have shown is that LHX2 by itself is not activated by retinoic acid, but it is required to transduce the signal from the retinoic acid to activation of striate. And when we looked at striate in germ cells at E13.5, LHX2 high cells have high striate, whereas LHX2 low cells have low striate. And in striate knockout mice, LHX2 levels are not significantly different, telling us that LHX2 is upstream to striate, but downstream to something which is DAS-like. So we also looked at the entire transcriptome, which is known to be activated by striate. So striate is also like, it binds to a lot of oogonia genes, and it activates a whole lot of meiotic genes. These are known in literature. So we started looking at this 487 genes, which are known to be bound by striate, and striate is known to suppress mitosis and entry into meiosis. So these are 487 genes required. And this 97 genes are known to be activated by striate to let the germ cells enter into meiosis. And this is the data. So of the 487 genes in the LHX2 knockouts, about 20% of them were differentially expressed, 12% were upregulated in absence of LHX2. These are known to be activated by striate. So we think that in absence of LHX2, the striate repressed genes are not repressed correctly, and at least 4 of them genes were involved in pluripotency, telling us that now LHX2 is required to activate striate, and striate would then suppress pluripotency genes. And in the absence of LHX2 signaling, because striate doesn't correctly come up, it cannot suppress the pluripotency, not allowing the germ cells to enter into meiosis. And about 35% of the striate-bound meiotic genes, so these are genes which are absolutely to be activated by striate in presence of retinoic acid. In absence of LHX2, the striate targets are not correctly activated, and here's the RT-PCR for 2 of the direct striate targets. Both MSX1 and MSX2 are not correctly activated in absence of LHX2, telling us that in absence of LHX2, the striate doesn't get activated. Because striate doesn't get activated, the entry into meiosis is inhibited, and at the same time, suppression of pluripotency is inhibited. The final question that we asked was that so we said that LHX2 is necessary for germ cells to enter into meiosis, but is it sufficient? This was a more ambitious question that we asked, that if we just give LHX2 to the cells, can we just activate meiosis even in absence of retinoic acid signaling? A too challenging, a too over-ambitious experiment that we did. This is just a preliminary data, but I'm very excited by it. For that, we took GC1 cells. Unfortunately, we do not have any cell lines which are fetal ovarian germ cells. We cannot grow them in culture, and doing experiments on these gonads is difficult because they cannot be transfected. So we took these GC1 cells, which you got from Pradeep Kumar at RGCB. We took these cells, we transfected them with a construct which overexpresses LHX2. And as controls, there was an empty vector. And then after 7 days, we just assayed for the markers of meiosis. This is just qPCR data, but very exciting. LHX2 construct. Normally, these germ cells don't express any striate. Just give them LHX2, and striate comes up. So LHX2 was sufficient enough to drive striate expression. Not just striate, but even recate comes up when you just drive LHX2 in the developing gonads, and DMC1 in the germ cells, and LHX2 itself was sufficient enough to drive DMC1 expression. What Domdat further did was he added retinoic acid with and without LHX2, whether retinoic acid can do the same thing and do LHX2 synergize with retinoic acid. So when we give retinoic acid, we get activation of striate almost to the same levels as LHX2 alone, telling us that LHX2 is doing the business what retinoic acid is supposed to do to drive RA activation. And when we combine both of them, we get a real huge surge in expression of striate, telling us that LHX2 and retinoic acid cooperate to drive striate expression for the germ cells to enter into meiosis. Recate somehow does not follow this kind of a profile. Whether you have LHX2 alone, retinoic acid alone, or LHX2 plus RA, retinoic acid is activated at nearly same levels, and DMC1 also has the same profile. This tells us that LHX2 is not just necessary, but sufficient to drive meiosis in the developing ovary, giving them the oogonia fate and suppressing the spermatogonia fate. And probably these germ cells are suspended in pluripotency state, not knowing what to do. So this is a summary where we think that once the primordial germ cells enter into the gonads, they acquire a gametogenic fate, dazzle. This activation of dazzle is necessary to drive LHX2 expression. I've not shown you the data, but we have experiments to show that when you give retinoic acid or BMP2 to the germ cells, there is a tremendous activation of LHX2. And this LHX2 then drives these cells to exit from pluripotency and get into the meiotic program. And in the XY gonads, LHX2 is low because there's low retinoic acid, and this would then suppress the meiotic program and allow the germ cells to get into the spermatogonia program and get arrested into the early mitotic stage. So with this, I'll close the presentation. I'm very grateful to my students, my collaborators Shubha, Mohit, and Sarthak, who have worked very hard to give us a lot of data. Neha, especially Domdat, and Anshul, who have been working extremely hard to generate all this information that I've given you. And I thank ICMR and DBT especially for funding this project. Thank you so much, and I'll be happy to take questions. Yes, sir.
Nice talk.
Thank you.
I don't know whether you've seen the paper from Japanese group last year, which appeared in Developmental Cell. They have shown that in addition to STRA8, they have discovered a new gene, myosin,
Yes.
which is important both in the female as well as the male germ cell meiosis.
Yes.
You have not got an opportunity to score for the myosin yet?
We have scored for myosin. We have not finished the RT-PCR, so I wouldn't want to comment. But in our seq data, myosin is very, very low.
Okay.
So
See, both STRA8 and then the LHX2, I don't know, you said that you have been following our lab work.
yes.
Both of the genes are regulated by the link RNA, which we discovered in our lab,
Yes.
MRHL.
Yes.
Both these genes are regulated by MRHL. I don't know whether your data sets, what you are using from the literature, they are the data sets for the link RNA expression.
I have not looked at them. Thank you.
Because mostly you're looking for the protein coding genes. I don't know whether the data set must be including the link RNA also. It will be worthwhile looking into the expression pattern of the link RNA.
Sure. We will have a look. Thank you for that suggestion.
Okay.
Thank you.
Oh, one more addition. The STRA8 seems to be regulated by another transcription factor, SOX8,
Yes.
which is again regulated by our MRHL link RNA.
Yes.
So there's a lot. We have done mostly in the adult germ cells in the male,
Right.
but most of your data is in the embryonic stages, and more particularly to the female oogenesis.
Yes.
But the myosin is both relevant both in the oogenesis as well as spermatogenesis.
Yes.
Okay.
So we are also probing the same in the adult testis. We have not yet gotten there. We have just started looking at expression profiles of LHX2, and it starts in the first wave of meiosis in the adult testis. So we think that it is going to be conserved in both the places, but I'll definitely consider yours.
Nice work. Nice work.
Thank you so much, sir.
Dr. Deepak, very nice. It's here.
Yeah,
Very
sorry.
nice word.
Thank you.
I was just wondering, in intersexes and problems
The
with
DSD.
gonadal development, would retinoic acid be playing a very important role, and could it have some, therapeutic kind of role one day?
Yes, so that's something which we have been wondering, whether women who are exposed to a lot of retinoic acid, do they have higher incidence of DSD, especially if it's a male fetus and taking a lot of retinoic acid. There is still no data correlating it that way. Unfortunately, the sensitivity to retinoic acid is very narrow. After E13.5 in the mouse, the sensitivity to retinoic acid is lost. So perhaps it might not work in a therapeutic way later on in life. But in the adult, as Sir has also said, that retinoic acid does play a role for exiting from the suspended mitotic stage to meiosis in the testis. So there perhaps it might do something.
Is gene LHX2,
Yes, sir.
it is located on an autosome or on the
It's on the autosome, it's chromosome 9. Chromosome 9. Yes.
Wonderful work. I was just thinking from the fly perspective.
Expected.
Okay. So, what it seems that LHX2, which is apterous in fly, right, is a master regulator, transcription factor. But what is the downstream signaling? What is STRA8? Is it another transcription factor? With whom LHS acts partner? Because my understanding is that they always form dimer or tetramer complexes. Any comment on this?
So that's something which we are now initiating. We are first doing a ChIP-seq for LHX2, but in the gonads, my students are refusing to do it, but I'll push them to do it. We are also wanting to look at the protein partners, which is another challenge for the size of the tissue. So maybe we think we'll start that work at least in the GC1 cells to know what's happening, because now we have a model system in hand which could work much better. In the brain, there are several partners known for LHX2, but none of these are expressed in the gonads. So we took all the data from Shubha's lab, the partner proteins, trying to see are they expressed in the gonads, but unfortunately, none of them seem to be doing it. So right now, probably there are something very different sets of molecules doing the same thing there. What we suspect, one of the things is that Shubha's lab has shown that it partners with DNMT, one of the DNMTs, to allow demethylation. And demethylation events are also very crucial for germ cell to enter into meiosis at this stage. So that is just one cue that we have right now. But right now, there's no data that we could.
But coming back to signaling, at the end, out of the 756 signaling, one of them is pro-male and pro-female germ cells. Any thought on that?
Not really right now.
You want to ask a Drosophilist?
Yes, I mean, first the Drosophila people need to tell me whether Apteris knockouts have gonad development defects. I think Apteris has been retired by the Drosophila guys completely. Nobody. Absolutely. And what gives them those identities, we have no idea. Yes, we should. That's. Honestly, we have never thought in that direction, but one thing that consistently pops up in our RNA-seq data set is BRCA. So that's one which is highly upregulated in absence of LHX2. So maybe there is a connection, maybe we can, I need to think. Okay. I'll think of it. Thank you for that suggestion.
I'm sure there are many more questions, but Dr. Deepak is with us for the rest of the day. Thank you, sir, for such an enlightening talk. May I please request Dr. Swati to present a memento to Dr. Deepak? Thank you once again, Dr. Swati. We'll now move towards lunch. I'm sure everyone is hungry. The lunch is organized in the hostel area. There are volunteers who will direct you to the hostel area. But before going to the lunch, no one is allowed to get a lunch plate until we get group photograph at the steps of the hostel area. Please, I request everyone to be there for the group photograph. It's very necessary, especially all the students and all the senior faculty members, and everyone should be there. Thank you. Yes, now, before the lunch, you're not going to get a plate if you don't get in the photograph.
How many of you, no, we have to tell, is he one or not is the next question to wake you all up. Yes, how many of you? Okay. Yes? Okay, very few. But when you speak, let's see, okay? Anyway, so having you all woken up, this is Dr. Raghu, as you all know now, and he describes himself as a Bangalore boy. Spent almost all his life here, except the other part of his life has been spent in Cambridge, okay, UK. So we are very fortunate to have him because he's one of a kind in the country. He did his bachelor's in MBBS, that is medicine, and then he went on to do a PhD from NCBS. Okay. What were his interests in MBBS which took him to do a PhD? He will share as part of his lecture today. But having joined PhD, he worked on cell signaling and cell communication were some of his major interests from that day to this day to today, though he has expanded on various other aspects over time. So he worked on cell signaling, particularly calcium signaling at various aspects, and then got his PhD with Dr. Gaiti Hassan. And he's also famous because he's one of the earlier batches of PhD students in NCBS, okay, pioneers. Okay. And then he went on to do postdoctoral work at Cambridge University, where he also continued to look at calcium signaling, but he looked at it in the context, not only that, but a broader question of signaling in vision. He looked at that, particularly GPCR signaling, which I'm sure you all know is a prominent player in vision. There are any of those contributions, you may have read papers, are milestones in vision research, the first few papers in elucidating signaling in vision. And one of them is also Raghu's work. Okay, so we are very delighted and excited to have him here. And he's back. He was back to Bangalore in NCBS, and he's been there for over a decade now, and worked on various aspects, particularly the same cell signaling and communication being his focal theme and interest, but has expanded to many other areas than what I told you. And also, I must mention that he was and is a fruit fly biologist as well, in addition to being an MBBS degree holder, and much of his research has been done using Drosophila as a model system. Okay, in addition to his research, which we are going to hear about today, he has had made profound contributions to education in the country, and he's a professor there and also dean of research in NCBS. He has not only developed several research activities, but also deeply strengthened the ties of research that come out of interactions between clinicians and basic scientists there, and brought in new programs at NCBS, particularly those in collaboration with RGUHS. Okay? Of course, he has been a great mentored many PhD students, both at Cambridge, where also he was a faculty member in addition to a postdoc after postdoc, and here. And he has contributed in many ways to other activities in science. And in the interest of not taking away the focus from his lecture and his work, I shall stop here and request Dr. Raghu to give us his lecture, which will be on various aspects, as I understand, on human diseases and metabolism and development. Okay, welcome, Raghu.
Yeah, okay. Yeah. Okay. Good afternoon, everybody. First of all, thank you to the organizers for inviting me to give this talk. As was just mentioned, most of my life I worked on flies and looked at various processes using flies. But when I was invited to give this talk, I thought I should speak something about my work on human neurodevelopmental disorders, as it's particularly appropriate to the theme of CHG. So, like most students who go to medical school, when I arrived in medical school, I didn't really have an idea of why I was there. So one goes to the class and listens to the lecturers, and then you have tests and exams and so on. But about 6 months after I entered medical school, this gentleman walked into the classroom
Professor Prakash Shetty. He was the professor of physiology at St. John's Medical College, where I did my MBBS. And he shocked us by starting off by saying that everything you need to know for the exam is in Guyton's textbook of physiology. So please go and read it. I won't be teaching any of it while I'm here. But what he said he would do was to explain to us the difference between knowledge and the manner in which that knowledge is arrived at or derived, which of course we call research. Now, having come from a background where there was no science in my family, this was very new to me. I did not have any idea about this. And so I listened very carefully to him. And what he did was to describe the work of this very famous scientist, Dr. Bernardo Houssay. How many of you have heard of him? Well, he was an Argentine physiologist, an MD. And what he did during his career was to work primarily on the mechanisms by which various tissues in the body signal to each other. And his stock in trade was to develop models of various deficiencies relating to the endocrine system. And he was amongst the earliest scientists to induce acute deficiency of hormones produced in different parts of the body. And Dr. Houssay got his Nobel Prize for discovering the role of the anterior pituitary, or the anterior hypophysis as it is called technically, in the control of blood sugar, which until then was thought to be primarily controlled only by insulin. So I thought this was all rather nice, and I got attracted to the idea that one might understand a complex problem better if you could break it down into simpler things and generate models that allow you to understand individual processes that underlie human disease. So all of us have fallen ill at some point or the other. We go to the doctor, and the doctor then does a number of different tests. These include clinical biochemistry. They might do an MRI on you, a CT scan or whatever. Or they might do something like a physiological measurement. But really, the purpose of doing all of these tests, to which many of you would have been subjected, is to have a readout of or a report of what is occurring in the body, which in fact is the top end of a number of processes that start from individual molecular changes in the cell, which integrate into altered cellular function, leading to organ dysfunction, and finally manifest in the clinical symptoms for which we originally went to the doctor. So this is good, and there are many tests that are available, and some of them you heard about this morning. But in fact, one could be more precise in the diagnosis of a disease and its treatment if you could understand in much greater detail what the cellular and molecular changes are that ultimately lead to disease phenotype. And for many diseases, you can do this, but the brain presents a particular problem in the sense that if you have a disorder of the blood or even of the kidney or the liver, a doctor can, or a pathologist who's skilled, can take a biopsy and then study the processes that underlie the disease. But in the case of the human brain, it is not possible to do a biopsy on a living person, and therefore one is restricted to understanding disease by observing from outside rather than intervening and looking at individual cells. So I'll talk mainly about my work on neurodevelopmental disorders. So this is the global burden of disease, which is an audit of diseases that happen, of different types of diseases in all parts of the world. It's published at frequent intervals, the last one around 2019. And this is about mental illness in humans. There are about 193 million people in India who have some form of mental illness. The most common one of that is idiopathic developmental intellectual disability. And this refers to a range of symptoms that are manifest in young children and young adults that deviate their behavior or slow down the development of their social skills, etc., and intellectual ability as a function of time. So from a clinical point of view, there are different ways of classifying neurodevelopmental disorders. This particular one that I've shown here relates it to etiology and factors that act in the prenatal period, such as nutritional deficiencies, infections, toxins in the environment, etc. Then there are other ones such as perinatal, for example, trauma, birth asphyxia, birth trauma, etc. And then there are postnatal factors as well. But as you can see, many of these are quite general things, and it is often quite tough to work out what was the etiological factor and how did it lead to altered brain function that has resulted in illness in the young child. There is, of course, some groups that are better defined, and these include single gene disorders such as the ones shown over here: Cornelia de Lange syndrome, lissencephaly, NF1, and so on. And the attractiveness of these sorts of disorders, apart from the clinical importance, is that they allow you a controlled environment or a controlled setting in which to try and work out what was the alteration in brain development that led to the phenotypes that you see in the young child. And the value of understanding such things is that it then allows you to try and work out what might have gone wrong in some of these other cases where it is environmental and nutritional factors rather than genetic causes that led to altered brain development. One thing I'd like to point out is that the human brain is one of those that is not complete in development at birth, and up to the age of 18 continues to develop, refine its connections, and therefore there is indeed an opportunity, if one can understand the disease, to try and intervene clinically and improve the quality of life for that patient, even if it is arising out of a genetic disorder. And I think you've heard some examples of that with the glycogen storage disorders this morning. So the overall objective of the work is to understand how the mammalian brain develops in a normal situation and how brain disorders deviate from this normal function. And if we can do this, one can not only understand the fundamental processes that lead to the development of the brain, but also what goes wrong in brain disorders. Now, with all these generalities, I'll go to the disease I'll describe today, oculocerebrorenal syndrome of Lowe, otherwise called Lowe syndrome. It's a very, very rare disorder. It would never make it to any list that is curated by the government. 1 in 100,000 or greater. Only 3 organs are affected: the eye, the kidney, and the brain. You get a congenital cataract, which doesn't recur if you replace the lens. Low molecular weight proteinuria, and essentially features of a reabsorption defect in the proximal tubule, and a range of brain disorders or brain phenotypes, such as ranging from mental retardation, seizure susceptibility, cystic lesions in the brain, hypotonia, and behavioral problems. Lowe syndrome is not lethal. In modern times, children live all the way up to the age of 30 or so, where typically the cause of mortality is renal failure. This is a set of MRI scans from the brain of a child with Lowe syndrome. You can see that at 2 years, the brain is relatively normal, but by the time the child is 6 years old, you start seeing the appearance of these lesions in the periventricular region, which are hypoechoic in nature and which are very characteristic of the disease. But I should emphasize that this is not a disorder in which the brain is either smaller in size or larger in size, and there is no primary hydrocephalus. So the OCRL, the mutation, the gene underlying Lowe syndrome has been identified a long time ago. It encodes an inositol polyphosphate 5-phosphatase. It's located on the X chromosome, and there's been a huge amount of work from all over the world in trying to look at patients. Each of these dots is an individual patient. And you can see that the mutations are distributed across all the 23 exons of the gene, with a vast majority of them being in the phosphatase domain, which is the core functional domain of this protein. The OCRL gene is part of a much larger gene family of 5 phosphatases in humans. There are 10 genes in any mammalian genome, including the human one that encode for 5 phosphatases. In simpler organisms, for example, like the fly, each of these classes, which is shown in a black line over here, is represented by a single gene. And so in some senses, in the mammalian genome, these have been duplicated to provide much more sophisticated control of function in individual tissues. So why do you need an inositol phosphatase? So phosphatidyl'inositol is shown over here. It's a very low abundance lipid found in all eukaryotic cells. It can be differentially phosphorylated at positions 3, 4, and 5 to give you 3 monophosphates, 3 bisphosphates, and 1 tris phosphate. And then these are distributed at different membranes of a normal cell, and they serve many different functions, which are shown over here. This over here is the oldest known function, also the one on which I worked as a PhD student. It serves as the substrate for the production of IP3, which is a key regulator of calcium signaling. But it also controls many other processes, such as the regulation of the cytoskeleton, membrane trafficking, and most ion channels and transporters in the plasma membrane require phosphoinositides as an obligate signal for their activity. Now, these phosphoinositides are produced by kinases and phosphatases. Each arrow shown over here is an individual kinase or a phosphatase, and these enzymes are exquisitely specific for the substrate on which they will act, and also equally specific for the position on the inositol ring on which they will add a phosphate. And so that's the manner in which you generate and degrade these lipids, which are basically signaling molecules. Now, when phosphoinositides were discovered way back in the late 60s and early 70s in the last century, it was found that they were particularly enriched in the brain. And this is really just a collation of various different disorders in which one or the other enzyme involved in the metabolism of phosphoinositides is implicated. And you can see many genes and many diseases over here that will be familiar to people working at CHG in the clinical setting. I'm going to talk today about Lowe syndrome, which involves one such phosphoinositide phosphatase. And the substrate of Lowe syndrome is PIP2. It's found on the plasma membrane of every cell in your body. Indeed, every eukaryotic cell has PIP2 on its plasma membrane. And is absolutely essential for the function of the cell, because if you delete the kinase that makes PIP2, the cell is not viable. OCRL has been found in every organelle in the cell, and there are a number of subcellular processes that have been implicated as requiring OCRL activity. But if you think about all that I just said, you might imagine that people with Lowe syndrome might not even make it through the early stages of development. If a gene is supposed to be required for cytokinesis, it's unlikely that it will go through the whole of development. So it's expressed in every cell. The substrate is an essential determinant of the plasma membrane. But then there are several points that are clearly not explained so far. Why is the disease not as severe as we might expect it to be? Why are there only 3 organs affected, namely the eye, the kidney, and the brain? And lastly, and most importantly, the problem of phenotypic variability. I'm sure that clinical geneticists recognize this, but the average scientist doesn't, so I'll just write it here. I've written it down here. There are patients, although it's a single gene disorder, there are patients with severe renal symptoms, but very mild neurodevelopmental phenotypes. There are also patients who are just genotyped for severe neurodevelopmental delay, but with almost no abnormal renal function. And finally, there are patients who have simply only renal function, and that to very mild renal function deficits, and no other symptoms at all. And this is a collection of 7 or 8 patients from the Bangalore area who are genotyped in various centers for various purposes. You can see this one over here is a male boy. I'm a male of 4 years of age. He has phenotypes both in the kidney, the brain, and the eye. It's a classic case of Lowe syndrome. On the other hand, in yellow, you can see 2 individuals who have only neurodevelopmental phenotype, but no renal phenotype whatsoever. And conversely, here is an example in blue of a child who was phenotyped for nephrotic syndrome, which is a high proteinuria disease, but he has no neurodevelopmental phenotype at all. And at least from a clinical point of view, it would be most helpful if you had a young child in which you could predict what would be the cause of the disease, and therefore how should you plan to manage this child? Should you focus on the renal symptoms? Should you focus on the neurodevelopmental disorders, or both? And if you could understand why there is this variability, then that predictive power becomes a possibility. So we identified a family in Bangalore some years ago affected with Lowe syndrome. Here is the pedigree. There are 2 identical twins who have the disease, as well as a single cousin who also has the disorder. The initial clinical diagnosis was done on the basis of a cataract, the renal problems, and intellectual disability associated with an X-linked inheritance. And so people in my lab, in the lab setting, sequenced all 23 exomes of the OCRL gene. We identified a mutation, a stop codon in exon 8, and when we express the cDNA in Drosophila S2 cells, you can see that it makes a truncated protein lacking the phosphatase domain. And the mutant protein is now diffusely distributed in the cytosol as compared to the punctate distribution of the wild-type protein. So in order to understand the mechanisms underlying the disease, or the cellular mechanisms underlying the disease, we requested the family and obtained permission from them to collect blood cells and generate induced pluripotent stem cells from all the 3 patients and both the sets of parents. And the idea was to create a resource that would allow us to ask several questions in regard to Lowe syndrome. So the iPSC lines were characterized. I won't go through the details, but they express all of the expected markers. This is the karyotype, and you can differentiate them into embryoid bodies and then find markers representative of all the 3 germline layers. I'll address a couple of questions today about OCRL. First of all, the biochemical phenotype of OCRL, which had never been seen in the brain, and certainly only in one case in fibroblasts from a patient in the United States. And related to that, the mechanism of compensation, which might result in a milder disease phenotype. So the OCRL enzyme converts PI45P2 into PI4P, and therefore what you might expect in a patient that has a loss of function mutation is that the levels of PIP2 will rise and the levels of PI4P will fall. And so what we did was to take the iPSC lines and from each of the 3 patients and a control, which is D149. This is a control line from an Indian person of the same genetic subtype, and measure PIP2 levels. And what you can see is that all 2 of the 3 patients have elevations in PIP2 levels that are clearly apparent but are not spectacularly high. So you don't see a 10-fold rise in PIP2 levels. If you take these iPSCs and differentiate them into neural precursor cells, which is what gives rise to the brain ultimately, you once again see that in the patient LPSH004, you see that the elevations in PIP2 levels are now much less than it is over here. Surprisingly, the levels of the substrate were also elevated in the iPSC lines, but had almost become normal by the time you get to neural precursor cells. So we also generated reporter constructs that allow you to measure PIP2 levels at the plasma membrane with single cell resolution. And this probe on the plasma membrane here in red reports the level of PIP2. If you compare the wild type with 004 and quantify a few hundred cells, what you find is that once again, the level of PIP2 at the plasma membrane is indeed elevated in the OCRL patient compared to the control cell line. And this is at the neural precursor cell stage. So what the bottom line is that it appears that the levels of PIP2 are elevated, not spectacularly so, and that over time, it slowly gets compensated. So what's the mechanism of the genetic compensation? So as I mentioned, there are 10 genes in the 5-lipid phosphatase family, 5 classes of proteins, all of which with the 5-phosphatase domain. And Bilal Akhtar, who did this work, what he did was to use qPCR and test the levels of each one of these 10 phosphatases. And when you look in iPSCs derived from the patient and compare it to controls, of course, you can see that in the level of OCRL in the patient line is dramatically downregulated. And there is a variable degree of compensation in each of the other remaining 9 phosphatases. Some of them are upregulated, and the other ones are modestly downregulated. If you do this experiment at the level of the NPCs, you now see that something quite different, which is that every one of the other 9 phosphatases is now upregulated to varying extents. But OCRL, of course, is still down in the patient line. And finally, if you take neurons that have been differentiated and maintained in culture for 30 days, you now see that the cell is totally decompensated. There are very few phosphatases that are upregulated that could take over from OCRL. And it's possible that that's why the patient gets through much of prenatal development, and the phenotypes are seen in the brain in the young child. The second point I want to address is the genetic basis of the heterogeneity in phenotype. Now, one of the reasons we picked this family over others is that it had a somewhat unique phenotypic characteristic and also a unique genetic structure. So these 2 are identical twins whose mother carries a heterozygous mutation for OCRL, whereas their single cousin, his mother is a sister of this lady over here, also carries the same founder mutation in OCRL. But remarkably, these 2 identical twins, their principal problem is that they have a very, very strong renal phenotype. And it is it is quite difficult clinically to keep them healthy and not require too much of intervention. They frequently end up in hospital needing care from a pediatric nephrologist. On the other hand, the single boy over here has almost no renal phenotype, but he has an extraordinarily strong neurodevelopmental phenotype. He's now 9 years old and has the mental age of a 2-year-old and has a vocabulary of just over 20 or so words. So given that all these 3 children have the same mutation in OCRL, why is it that there is such a variability in the phenotypic manifestation? So as was mentioned during the introduction, I am a Drosophila geneticist by training. The way I think is that way. And so it occurred to me that one way of thinking about this question is the following. So the problem is that LSPH004 has got a very strong brain phenotype, whereas 2 and 3 have a relatively mild phenotype. And you could explain this if the following way. If P4 inherits from their father or mother some variants that are not present in the twins, identical twins P2 and P3. And such variants could act as enhancers of the OCRL brain phenotype. Conversely, you could also argue that P2 and P3 inherit variants that from either the father or mother that are not present in P4 that act as suppressors of the OCRL phenotype. And finally, one could also argue that there are de novo mutations in the genomes of 2, 3, and 4 that by themselves act either as suppressors or enhancers of the OCRL phenotype. I should say that P2 and P3, not only are they identical twins, their clinical phenotype is identical as well. So to address this point, we carried out whole exome first and then whole genome sequencing. These are the statistics of the sequencing for those who like to look at it. And then we did 2 types of analysis. We carried out variant analysis for each individual sample. And we also carried out variant analysis for each trio, that is for each child and their father and mother. And from this analysis, we identified rare inherited variants, as well as from this analysis, de novo variants. And the summary of this study is shown over here. You can see that all 3 children carry varying numbers of rare inherited gene disrupting variants. That is, genes in which there is a stop codon, a deletion, or an insertion that would truncate the protein. They also carry variable number of rare inherited missense variants, amino acid changes likely to affect the function of the protein. And some of those are damaging in nature. So the variants shown over here are a subset of the variants shown over here. And finally, as you might expect, there are varying degrees, varying numbers of de novo variants, both coding and non-coding, in each of the 3 children. And these are defined as those variants not present in either parent using a number of bioinformatic criteria. Now, this is still a large number of variants to deal with. And therefore, what Hussein and I did was to try and come up with a system to prioritize variants. And what we did was to say the following. We have 3 tiers of genes in whom we would have variants to worry about. Tier 1 are those that are known to cause disorders, abnormalities, or phenotypes observed or very similar to that in Lowe syndrome. Tier 2 are those that are involved in biological processes in which OCRL plays a role. And Tier 3 genes are defined as those that are direct interactors of Tier 1 genes. And if you do this, then you automatically reduce from the 35,000 or so ORFs in the human genome down to about 15,000 or so. And then you can, and then they fall into these 3 different categories. And this pie chart here just also tells you which ones are ocular, which ones are renal, and which ones are cerebral. So what we wanted from our analysis were what are the damaging variants that are present in all 3 children, what are the variants that are present only in 2 and 3, and what are the variants that are unique to 004. And these were the ones that we are interested in. So first of all, disruptive inherited variants. So you can see here, this is the list of disrupting inherited variants, that is those that introduce a stop codon. You can see that there's a category that's common to all 3, the category which are present in the identical twins, and a category that's present only in 004. And of course, if you look at de novo variants, there is no particular pattern of inheritance. You can see varying numbers in each of the 3 children. You also find the same thing when you look at missense variants. This is a much larger list of missense variants, which is shown on the x-axis. The font is small because you would anyway not be able to read this large number. But the diagram does make the point clear that there is a large block of variants that is present only in 004, but not 2 and 3. And the reverse is true for the yellow block, which is all that present in 002 and 3, but not in 4. So I'll only talk briefly about the disruptive variants because we could go on forever otherwise. This is a list of the 7 disruptive variants found only in 4, but not 2 and 3. And you can see that what the genes are, their various functions that they perform in the cell. And in order to be able to focus on 1 or 2 of them, we also ask the question, which of these is expressed either in the fetal brain or in the adult human brain, or if it's enriched in the fetal brain or in the adult human brain. And there were 2 that came out phospholipase D4, and CEP290, which is a protein that is localized to the ciliary transition zone. So this is CEP290. It's a very famous gene. Probably have seen it in CHG many times over. It's a protein that is enriched in the brain, localizes to the ciliary transition zone, and is associated with a number of diseases that are normally show up in the clinics of clinical geneticists: US syndrome, Bartle-Biedl, Meckel, etc. So we wanted to ask the question, all of these bioinformatically predicted variants in genes, is any of them really actually altered in the patients? And so what we did was to ask the question, is there a difference in cilia structure or function in 004, not 3? And so for this, what was done was to take 2 independent markers of primary cilia and ask the question, if you plate NPCs and count the number of cells with cilia, what do you see? And it's apparent from here that in 004, that is the patient with the severe brain phenotype, the number of cells with cilia is lower compared to the control, regardless of which marker you look at. Remarkably, when you look at 003, which is one of the twins, the NPCs from this particular patient do not show the same reduction in numbers of cells with cilia with both of these markers. Now this, of course, could be because of many reasons, but we wanted to ask the question, is Lowe syndrome a primary ciliopathy? And it could be, because all the 3 organs affected are commonly seen in ciliopathies. And so for doing this, Bilal generated a knockout. He took a wild-type iPSC, NIH5, generated many years ago at the NIH, and he deleted the OCRL gene by introducing a stop codon in exon 8, which is the same exon in which the patient has the mutation. And you can see that it abolishes the expression of the OCRL protein. And then he counted cilia in NPCs derived from this iPSC. And what you find is that with both ARL13B and IFT88, there is no difference in the percentage of cells that have primary cilia. So how do we interpret this? Well, what it means is the summary is the following. So you have LS004, who has a mutation in OCRL in CEP290 and also a ciliary defect. You have LS003, who has the OCRL mutation, but no mutation in CEP290, and of course no ciliary defect from the experimental data. And in NIH5 and NIH, if you compare the two, OCRL has been genetically introduced in this cell line, but there is no defect in CEP290, and there's also no ciliary defect. So in other words, having a mutation in OCRL alone is not sufficient to give you the ciliary phenotype. Of course, the final test of this would be to look at the mother, the OCRL patient. She, of course, has no neurodevelopmental defect. She has no phenotypes whatsoever. But she does carry a heterozygous mutation in OCRL and CEP290. And of course, we do not yet know whether her cells have a ciliary defect. But I would be very surprised, because normally when you have that number of cells without cilia, you usually have clinical manifestations of a ciliopathy. So the last part of my talk, I'm going to change over to the real reason why we got involved in this, which is to try and understand the physiological basis for the neurodevelopmental defect. I won't go through the details, but basically we took neural precursor cells derived from the iPSCs and differentiated them using the principles of learned from a lot of work in neurobiology. And when you do this, you see the progressive expression of various markers, initially expression of shutdown of NSE markers, immature neuron markers appear, subsequently mature neurons, and then cortical markers, and finally markers of synaptic transmission. And you can take such cultures in vitro and maintain them for a long period of time. We can go up to about 3 months these days. And then you can load them up with a dye, that is live cultures, you can load them up with a dye. It allows you to report the activity of the neurons. And if I briefly play this video, you will see that there are various cells which are flashing on and off, like that one there just now and that one there. And this represents the spontaneous activity of the neurons. That is something that you see in the development of the nervous system in all animals, be it humans, in xenopus, flies, or worms. So you can do this across the time span of development. And as you can see, as you increase the age, the proportion of cells firing these transients progressively increases. And these are examples of the transients. You count a couple of hundred cells, you quantify the number of transients and the frequency of transients. And so what happens in OCRL? Well, if you take the patient's cell line and do the same experiment, what you find is that the frequency of transients in LS004 is lower than that in D149. Likewise, if you do the same experiment with neural precursor cells derived from LS002 and LS003, here too you see that the frequency of transients at an equivalent age is lower than that in wild type. So we did the same thing with the NIH5 knockout, that is the wild type cell line in which OCRL has been knocked out. And here again, you see that the number of transients is lower in the knockout compared to D149, which is the control. Now, I'm sure some of the students are wondering, why is he belaboring the point over 3 slides? The reason is that whenever you take iPSCs from patients and differentiate them, and you look for phenotypes, it is not hard to find a phenotype. But it is extremely hard to find a reproducible phenotype, because there are all kinds of effects that arise because of genetic background, because of the way you differentiate the cells and so on. But this, to us, therefore, is very gratifying that in 3 independent patient lines you can produce the same physiological phenotype. And if you take a wild type cell line and delete the gene, you can once again reproduce the same physiological phenotype. So we believe, therefore, that in the OCRL patient, as their brain is undergoing development in utero, the rate at which the brain is developing in terms of physiological activity is slower than that in wild type cells. The same thing has also been done using whole cell patch clamp electrophysiology. As the brain develops, the neurons start firing action potentials, initially immature ones, then progressively mature to give you repetitive action potentials. And this is a developmental profile of that. At an earlier age in vitro, you have many more immature action potentials and very few repetitive ones. You can see that over here. And as the culture gets older, you see many more multiple and repetitive action potentials. If you do the same experiment with neurons derived from 004, you can see that it is extremely difficult to find even 1 or 2 action potentials that are multiple, and very rarely do you see repetitive action potentials unless you maintain the culture for another 20 or so days. Most of the action potentials are either abortive or a single at equivalent ages of development. So the summary of this, of course, is that OCRL depletion results in delayed development of neural activity in neurons that as they're differentiated in the dish. The red arrow represents the fact that we don't know to try and develop a Drosophila model of OCRL. And so in the fly, for this particular class of 5 phosphatases, there is a single gene. And some time ago, using the now freely available technology of CRISPR-Cas9, we created a knockout of OCRL. You can see that this is a Western blot from fly larval extracts, and you can see that the protein is completely missing and can be restored by reconstituting with a wild-type transgene. The fly is in fact got a more severe phenotype than the human. There is developmental delay. The mutant larvae are much smaller than wild type, and there is a developmental lethality. Most animals will die during larval and pupal development, and there are very few escapers that eclose. These phenotypes can all be rescued by putting back the wild type OCRL gene into the knockout background. So one of the students in the lab was very keen to work out a phenotype for the brain disorder in the fly model. And so as I mentioned to you, there are many different manifestations in children with OCRL that relate to the brain. And one of them is that they are far more susceptible to fever-induced seizures than are normal children. And so Sukanta decided that he'd make an assay to try and model this. So it's very simple. Many fly people won't be surprised by these sorts of assays. Basically, you immerse a vial containing the flies into a water bath at 42 degrees centigrade, give them a heat shock. Wild-type flies will not normally be affected by this, but mutants that are susceptible to seizures, such as some of the ones that even Obaid worked on all those years ago, will collapse, and they'll have a seizure before they wake up, the function of time, and recover. And this is how it looks. So you'll see a set of vials being lowered into the water bath at 42 degrees centigrade. This is the mutant. These are some controls. You can already see that the mutant is rapidly falling to the bottom. And then if you take out the vials and keep them on the table, you can see that the mutants are all paralyzed, whereas the wild type controls are moving around quite freely. And if you do this experiment many, many times and quantify it, you can then calculate the falling frequency, the frequency with which the flies fall to the bottom, the fraction that are paralyzed, and also the time course of recovery from the paralysis. And this is what is plotted over here. You can see that the OCRL mutant rapidly falls to the bottom of the vial. The falling frequency increases as a function of time. And this is not seen in the wild type and is rescued by a duplication that restores the OCRL gene, a genetic duplication that restores the OCRL gene. The paralyzed fraction is also is seen over here. 80% of the flies at the end of the heat shock are completely paralyzed, and this can be rescued by putting back the wild type transgene. And the time course of recovery over here is shown, is also shown. Now the reason why we needed to do this, apart from generally being interested in flies, is that although iPSCs are available from patients, and you can even make cerebral organoids, it is not possible to do a physiological assay in the sense of behavior in using iPSC-derived models. And we wanted a living, moving, multicellular organism with a brain in which we could model some of the brain phenotypes of OCRL. And these types of experiments then allow you to do that. This is, of course, a full body knockout. And you can do the same thing using CRISPR-Cas9, this time driven by a GAL4 expressing Cas9 only in the brain. And this is Cas9 expressed only in the brain using, so this is DA-GAL4 that expresses throughout the body. You can see when you do it in this configuration, you can once again phenocopy what you see in the whole body germline knockout. And if you do the same thing, but this time expressing the Cas9 only in the brain, therefore only causing the deletion in the neurons, you once again see that the population falling is much more compared to the control. And at the end, the population that is paralyzed is almost 50% of the flies. This is, of course, much weaker than the phenotype of the whole body germline knockout, probably because of the variability of the Cas9. And the reason why one wants to do this is that this offers a model system in which one can now test the effects of various enhancers and suppressors that come out of the studies on the NGS sequencing on the human patient samples. So the summary is that I've told you that there is a neurodevelopmental delay in OCRL, and that's been demonstrated using iPSC-derived neurons in culture. It is not immediately apparent whether this arises primarily from a requirement of OCRL in the neurons, or it arises from some other cell type in the brain, which then affects the activity of the neurons. And this can now be addressed by co-culture of neurons derived from the patient with astrocytes derived from wild type, and the other way around, and so on and so forth. The subcellular pathology of OCRL is thus far unresolved. We have some work on flies that indicates that endosomal trafficking and enhanced lysosomal function might underlie this, but this is not, it's not fully resolved. We are now testing the contribution of individual genetic variants to enhancing or suppressing the brain phenotype using a combination of the cell lines as well as the flies. And then one can test the in vivo significance of these using the fly model and the behavioral assays of the sort that I just described. So what I've told you, of course, is about a human disease which we have modeled in the fly. And sometimes that's not good enough. One needs to typically sometimes go back earlier in evolution. And for some diseases and some genes that we work on, we often look at the earliest multicellular organisms that are there in which the gene is present, typically things like coral and choanoflagellates and so on. And we feel that a full understanding of human disease will come not just from studying the patients themselves, but also by making suitable models in simpler systems that might allow you to better understand what was the earliest function of the gene and how did it evolve into humans, and therefore how does it function over there. So this, like Deepak mentioned this morning, I finished in about 40 minutes or so, but all of this work took about 7 or 8 years. A large number of people were involved in doing this. We would never be able to do any of this work if we didn't have all of these central research facilities at NCBS. This was a close collaboration with Anil Vasudevan and his clinical team. They work very, very hard to look after these patients. I must say that I would particularly like to thank the patients and their families, the parents of these children affected by Lowe's syndrome are fully aware that none of the work we're doing is going to ever help their own children. But somehow they're happy to participate because it might help other children in the future. We're also looking to extend this cohort and derive some general conclusions about phenotypic variability, for which we are working with various pediatric nephrology departments to try and get more trios in which variants can be mapped and severity compared. And this work was funded by a number of different people, NCBS, the India Alliance, DBT, and the Prateeksha Trust. So I'll stop here and answer any questions. Yes, I didn't want to give a long extended talk, but we have made a separate story on the renal phenotype of OCRL, which we have modeled using pericardial nephrocytes. And there what we find is that if you delete OCRL specifically in the pericardial nephrocytes, you can mimic the subcellular defects in OCRL patients and also in the whole body knockout. Pardon? So basically what you see in OCRL mutant cells is that the early and late endosomes are downregulated and also mispositioned in the cell relative to where they normally are. But the number of lysosomes is dramatically upregulated, as are the number of autophagosomes. So this can be reproduced in multiple cell types in the fly, as well as in the iPSC-derived cell lines. The significance of this is not known. But anyway, in the nephrocytes, there is also a reduction in the uptake of dextran and other markers from the hemolymph into the nephrocytes. Now in flies and in many organisms, the kidney is required to deal with heavy metals. And in flies, you can do this assay where you grow the larvae in silver nitrate. And then the nephrocytes take up the silver nitrate and clear it, and it appears in the urine ultimately. So this is blocked in OCRL knockouts. Can be rescued by putting back the wild-type Drosophila gene. It can be rescued by putting back the human wild-type gene, but it cannot be rescued by putting back the patient gene from the same family that we have studied over here. Yeah. So, I mean, the importance of this is that unlike this particular mutation, which is a stop codon, and therefore there is little doubt that it is pathogenic, there are, of course, many variants that are picked up in NGS sequencing whose functional significance is unclear. And so having a fly model of that type allows you to evaluate the significance of variants coming from NGS sequencing in terms of how they might actually affect function. We've done this not just for OCRL, but for nephrotic syndrome as well. And it's a very valuable thing. I mean, from the time Anil tells me about a particular variant to the time I can give him an answer is only 4 months. And the treatment of nephrotic syndrome, the management of nephrotic syndrome in children is a process that occurs over many, many years. And therefore 4 months is a relatively short delay in which a clinician can expect an answer from me that informs his management of the patient.
This may be related to a point you had made earlier. The question is, are there phenotypic variations that you might not be able to see in single neurons, but in neural networks?
Yeah, thank you for asking that question. I showed you the development of neural activity as monitored by calcium transients up to about 60 days or so. By the time you get to 70 days, you find that networks have formed in the dish itself, and that all of the neurons are firing transients synchronously. So if you monitor all the cells in the dish as a function of time and plot them, you will find that the transients are firing synchronously, which is typically taken as an indication that there is a neural network that's formed, or a network of neurons that is synchronously firing. So it is possible to look at that. I must say that these children with OCRL, they don't have a very big defect in either the structure or connectivity of the nervous system, not as measured on the MRI or the CT scan. I mean, these boys, if you see them, they run around everywhere. They're perfectly active in all sorts of ways. The problem is that they have a cognitive defect. And that can arise from some very subtle changes in the development of the brain. Indeed, it can be just a slight delay in development so that synaptic connections are not formed at the right time in the right place. So it could affect network formation, but it will require us to maintain these cultures for a longer period of time, up to the point that the neurons are firing synchronously, and then compare wild type and patient derived cultures side by side. So I think that's what that may be a first approximation answer to your question.
Perspective, I've got a couple of patients. They all seem to be very tiny, and the ones that we have had, they've not come from nephrology. They've come for developmental delay that we assessed, and we managed to find this, and then found that they had proteinuria or RTA. And they've been managed reasonably well from a kidney perspective. And they seem to have responded very well to developmental modulations, but they seem to have a particular behavioral phenotype as well.
Yeah. So, OCRL is a very old disease. It's been around for a very long time. But it has never been clear. So the children are all smaller than normal children of the same age. It's never been clear whether the smaller size of the children, and actually you see that in the fly model as well, they're smaller.
They're so small.
Whether it arises from a requirement of OCRL in every cell in the body, or whether it is a secondary consequence of a nutritional deficit arising from altered kidney function. So of course, if you have proteinuria, you might expect the child to develop, let's say, less than a wild type. So this is the reason actually why we developed this CRISPR-based strategy of deleting the gene in question, in this case OCRL, in specific cell types. And there's already an answer. So you see the Drosophila larvae that I showed you, the germline knockout. They are very evidently smaller than the controls.
I can see that, yeah.
But if you take the Cas9 and express it only in the nephrocytes, and we can show experimentally that there's been a deletion of the gene, you can reproduce the renal clearance defect, but the larvae are normal in size.
They're normal in size?
They're normal in size. So this means that the growth defect is not secondary to the renal defect, and that there is a separate locus or a separate tissue in which it is required in order to control growth. And I don't know what that is at the moment. But if you delete it, for example, in different tissues and try to phenocopy the growth defect, it's possible that one can identify that tissue.
I think there are no more questions. Thank you, Professor Raghu, for the enlightening talk, and I'll request Dr. Sudha Srinivasan to hand over a memento, please. I'm sure all of you are still awake, at least 1/4 or half. I've been given the task to introduce our next speaker, who is Dr. Sunil Bhatt. Dr. Sunil Bhatt he is a person who has traveled from north to south. He has finished his MBBS and MD Pediatrics from Jammu Medical College and has been awarded the gold medalist also throughout his MBBS and MD Pediatrics. He has also been awarded the Dr. Nanak Chand Gold Medal 2000 bestowed by the President of India, His Excellency Abdul Kalam Sir. Moving forward, he went to Delhi to finish his fellowship in pediatric hematology and oncology and bone marrow transplant from Sir Gangaram Hospital. Then there's nothing left in the nation, maybe. He moved to Australia and he finished his fellowship in pediatric oncology in Sydney, Australia, along with some advanced fellowship. He has been awarded the gold medal and the outstanding student throughout his fellowship also. Presently, he's the director and the head of pediatric hematology, oncology and bone marrow transplant at Narayana Group of Hospitals, Majumdar Source Center. He is also the secretary of Karnataka Pediatric Hematology and Oncology Society and the editor, International Journal of Pediatric and Oncology. His primary interest is in bone marrow transplantation in children, including the newer techniques like haploidentical transplants using alpha-beta TCR depletion techniques. And I think he has experience of more than 1,000, around 1,200 transplants in children, and almost approximately 60 publications in many journals and many chapters in many books. It's an honor, sir, to have you here, and we are looking forward for your talk. Thank you, sir.
Very good afternoon, and it's always a pleasure to be here. But sort of very daunting and intimidating, with so many basic scientists sitting and listening to you. They always say that when you're speaking on a topic, you should presume that you know the maximum out of all the people sitting in the audience, but I always have a feeling that I'm the least learned whenever I come here. So I think we'll change gears, and we saw a lot of translational work and amazing work which Dr. Raghu just showcased. It will be more of a clinical perspective of how we can manage some of these some of the genetic disorders, and bone marrow transplant is one of the treatment options for some of these, and I think we'll just take you through the journey of how we have been able to help some of the children who have been diagnosed with genetic disorders, and how bone marrow transplant can be curative in some of them. So before we do that, I'm just going to show you a case which was a 16-month-old baby who presented with nausea, gaining weight, and had multiple swellings all over his body. He had abdominal distension for 6 months when he presented to us. A very interesting family history. He was from a second-degree consanguineous marriage, the only living child in the family, because the older two siblings who were born to this family had developed BCG lymphadenitis and died at 6 months of age. Fortunately, with this history in the family, this child was not vaccinated after birth. He was well till 9 months of age, but after that he started developing recurrent pneumonias. Because there was a family history, he was straight away starting anti-tubercular drugs, although it was not proved to be tuberculosis. There was no response. He continued to have failure to thrive. He had these swellings all over the body, which were increasing in size as the weeks and days passed by. This is the child when he presented to us. He was pale. He had the generalized lymphadenopathy, and cervical lymph nodes were quite significant. And he had a very typical rash. It's not very visible on the picture, but it had a very typical rash, which was erythrodermic, and he had a big liver and spleen on examination. As we would do for evaluation of such a child, we his hemogram showed a severe anemia. His hemogram was very low, a very high white cell count, and the other evaluations which would you do for recurrent infections, organomegaly, lymphadenopathies was ANA profiles, torch profiles, tuberculosis testing, HB electrophoresis. That was not conclusive of anything. We ended up doing a liver and lymph node biopsy of this child, which showed nothing really much. It showed lymphocyte infiltration, and CD20 are the B lymphocytes, and the CD5 and CD3 are the T lymphocytes. So he had a lot of T lymphocytes actually in his paracortical areas in the lymph nodes, and that was the only clue we got from his biopsies, and it was not helpful either. There was a history of 2 sibling deaths with an infection which should not have been there. BCG is a very, very I would say non-pathogenic bacteria in an immune competent patient. But with the primary history in the 2 siblings, we did suspect primary immunodeficiency. There are 2 immunodeficiencies which kind of present like this: chronic granulomatous disease and leukocyte adhesion defect. So these were worked up and they were normal. His immunoglobulin levels were normal, suggesting that his humoral immunity, which is given by B cells, was normal. T functions were sent to NIH Mumbai. It's many, many years ago. It's almost 8.5, 9 years ago. This case we looked after. At that point of time, we didn't have a good evaluation setups here, and NIH Mumbai offered to do the lymphocyte subsets as well as the functional aspects of the T lymphocytes. The T and B lymphocytes and the NK lymphocytes were all normal in number. So the number was not a problem, but the functionality of the T lymphocytes was a problem. The T lymphocytes were not proliferating to the stimulus, to the antigenic stimulus. And what they found is that the proliferation response to anti-CD3 and anti-CD28 was very low as compared to the abnormal to a control. And we repeated 2 different occasions because the sample had to travel to Mumbai to get this functional assays done. And both the times it was found to be suboptimal. So we diagnosed this patient as a T cell functional defect. At this point of time, of course, we don't know the genetic etiology, we don't know the mutations which this child is having, but we know that functionally the T cells are not functional, and that's what would explain the whole phenotype in this child and probably in the older 2 children as well who were diagnosed with BCG lymphadenitis. So we knew that this child needs a transplant to cure because the T cells are not functional. It's exactly like Glasman thrombasthenia, which some of you must have read and come across, where the platelets are normal in number, but they are not functional. So similar phenotype was here as well, which was related to the T lymphocytes. So we required a bone marrow transplant to cure him, but there were no matched donors in the family. There were no siblings who could donate for him. There were no unrelated donors who could donate for him. So we chose to take one of the parents as a donor. But at this point of time, as I said earlier, we don't know the genetic etiology. As we all know, immunodeficiencies either are autosomal recessive or X-linked, most of them. To be on the safer side, the worst case scenario could be the mother is a carrier of the gene, so we didn't want to take mother as a donor, and father probably is a carrier, and carriers can be used as donors, so we took father as a donor. And this is the child transplanted with his father's stem cells. There's the same boy 1 month post-transplant. He has engrafted. His hematological recovery has happened. His chimerism, which is the donor cells in his body, is 100%, and he has put on weight. The rash is resolved. His automobile is resolved, and he looks like a completely different kid now, and is cured of his T cell functional defect, which was his primary disease. And it's a little older slide, but it's about 6 to 7 years post-transplant. Now it's cured. Now, while we're looking after this kid, and we were evaluating, his mother was pregnant at that time, and she was pregnant in 22 weeks. We didn't have antenatal diagnosis to offer, even though she was, earlier in the first trimester, we could have done anything different. But we just explained to the family that, there's a risk that the 4th baby may also be having the same disease. They chose to continue the pregnancy because we explained them it's most probably autosomal recessive, and they wanted to take the chance. And anyways, it was 22 weeks anyways, so couldn't do much. So the 4th baby was born, and unfortunately, the 4th baby also the same T cell functional defect. So 4 children, all the 4 children affected with a T cell functional defect. And the 4th baby also had a transplant using the same stem cells from the father, because when we did transplant for this baby, we had stored some of the stem cells, and that baby is also cured of his T cell functional defect. Now, before this child was transplanted, we had stored some of his blood samples and DNA, and one of the labs, it's after transplant, in fact, with the labs here in Bangalore. It's many years ago, and we didn't have good access to sequencing those days. And they offered and they identified a mutation in interferon receptor gamma 2. And this was a novel mutation which we have published, in fact, and that was the pathophysiology behind the T cell functional defect. As we know, interferon gamma receptor 2, interferon gamma is a very important cytokine which helps us to fight especially bacterial, especially viral and tubercular infections, and that would explain the whole phenotype in this family. So this case was to highlight how the genetic diseases, one, can be such a disaster for the whole family, you can imagine the family's journey through all these years with dealing with 4 sick children back to back with a very dreaded disease, and killing a couple of the initial two children with this disease, and also to highlight that how treatment, a stem cell transplant could change not only the lives of these children but also the families they belong to. So that was just a case to set the tempo for today's talk. And bone marrow transplant or a stem cell transplant is not a new treatment. The first transplant was done in 1958 on a child. I'm a pediatrician. I take a lot of pride in saying this, that a lot of contribution in transplant world has been from pediatrics. The first child who was ever transplanted was a kid with ALL, acute lymphoblastic leukemia, and he had a transplant with identical twin. In 1958, with a gentleman who was considered as father of stem cell transplant, Esau Donald Thomas. But what happened post that, the second, third, fourth, fifth transplant, they all failed. This was happening in Seattle, USA, and they all failed. these patients used to get severe diarrhea, liver dysfunction, and skin rash, and they would die after 7-8 days of transplant. So we didn't know what's happening, and they named this phenomena as second disease. Second disease is something else they're developing after transplant, which they didn't know. So the transplants had to be stopped, and they went. Had this been that the first was not a successful transplant, probably the transplant had never seen the light of the day if they had started from the second, third, fourth, fifth patient. So they went to dogs and identified something called as dog leukocyte antigen system, or DLA, and then came back in humans and identified something called as human leukocyte antigen system. I'll explain the next slide what that means. So human leukocyte antigen system was not known in the first transplant, and because of identical twin, and it was successful because probably they were HLA matches, which we didn't know. The second, third, fourth failed because HLA match was not there. Although they were family members, they were not HLA matches, and they died with very severe graft versus host disease. Now, it took another 10 years to, so the transplant activity starts again, and mainly in malignancies, but took another 10 years to have a non-malignant condition being transplanted. Again, a pediatric patient. This child was transplanted by this gentleman here called Robert Good. He's considered the father of modern immunology. And they transplanted a patient with severe common immunodeficiency. He was again a pediatric patient, and that was the first non-malignant transplant ever transplanted. And that set up and they set the stage and the agenda for transplanting non-malignant conditions, and immunodeficiency being one of them. In 1989, a first cord blood transplant was performed, and that was also performed on a child with genetic disease, and that was Fanconi anemia. Fanconi anemia at that time, this kid was a U.S. citizen. He didn't undergo the transplant in US because at that point of time, cord blood was not FDA approved as a treatment option in US. So he was flown down to Paris, where this lady called Ellen Gutman, who performed a transplant on this child with Fanconi anemia, and that child now is almost 40 years of age and is cured of his Fanconi anemia and is healthy and alive. So that was something about the history and how pediatrics has played a role, and how the genetic diseases kind of were started to be transplanted many decades ago. Now, coming back to HLA, one of the major differences between a bone marrow transplant and other transplants, which are solid organ transplants like liver, kidney, heart, pancreas, lungs, is that in a solid organ transplant, you do not require you don't require HLA compatibility between the patient and the donor. You require blood group compatibility. That's it. And of course, these days we can do transplants of solid organs which are blood group incompatible also, but that was traditionally the requirement for a solid organ transplant. But in a hematopoietic stem cell transplant or a bone marrow transplant, you do require HLA typing match between the patient and the donor. And as we all know, this is something which is which is like our fingerprint. We inherit these from our parents. Half comes from the mother and half comes from the father, and they're encoded on we have class 1s and class 2s, which are encoded on chromosome number 6. And the chances that your sibling would be matching you would be 25%, just a mental inheritance basically. So this is how low risk HLA typing looks like. A low risk HLA typing where you only know the antigen level match. And this example here of patient, these are the class 1 and class 2 antigens. And if you see this brother here is not a match, this brother here is a match, what's called a 6x6 match. This brother is a 4x6 match, and 6x6 is a full match and can be used as a bone marrow transplant donor. But when you are matching a patient with someone else who is not their biological sibling, even if it's a family member, parent, unrelated donor, you need to match them on a more in-depth HLA type. And that is not only antigen level, it also allele level match you need to match. And you also need to match on 10 different loci. In fact, now it's become 12 loci where you match the patient and the donor. So ABCDRB1 and DQB1 are the 5 loci where you need to match them, and that's how we report it as 5/10, 6/10, 7/10, 8/10, and 10/10 being the full match or a HLA compatible donor. So for biological siblings, a low original good HLA typing is good enough. But for anyone else who is not a biological sibling, you need to match them on HLA typing, and that's how on a high resolution, and that's why HLA typing is important in a hematopoietic cell transplant and needs to be kind of done before we subject them to transplant. Now, what we're talking today is that we're talking about stem cell transplant, and we also know that we have different other types of transplant, and we heard in the previous presentations also, some of the committed stem cells which you can work on. We have embryonic stem cells, we have mesenchymal cells, we have multipotent stromal cells, but we are not talking about them. Mesenchymal stem cells, in fact, there is some interest these days, especially mesenchymal stem cells taken from umbilical cord, tooth bud, adipose tissue, especially neurodegenerative conditions and some orthopedic conditions. They're experimental, and I'm not going to touch on that. I'm going to be talking on hematopoietic stem cells. These stem cells are committed to form blood or lead to hematopoiesis, and they lead to the white cells, platelets, and the erythroid production, and these are the ones which we need to be talking today. And hence, the more technical term for a bone marrow transplant is hematopoietic stem cell transplant, because that's what you are basically doing by delivering the treatment. Now, going on to what type of transplants are possible with hematopoietic stem cell transplant. One is something called as autologous transplant. That means you take the stem cells of the patient and give it back to the patient. I'll explain in the next slide why you want to do that. Or it can be allogenic. Allogenic means you're taking somebody else's cells and giving to the patient. Allogenic can be a match sibling. That was a traditional source of stem cells. That is a brother or sister is a match with the patient. That would be a traditional source of stem cells. That remained the source of stem cells for many decades, until we identified that there may be someone, maybe not in their family, but someone in the world who may have the same HLA typing as the patient has, and that's what's called as unrelated donor transplant. And that led to the conception of unrelated donor registries all over the world. So people like you and me who are healthy, they would put their HLA typing into the donor registries, and if a patient requires transplant, they will search the donors, the donor registries, and ask these donor registries to donate. So that's unrelated donor transplants. And nowadays, in the last maybe few years, we can now transplant mismatched transplants as well. And the most typical example being haploidentical transplantation. That means you take one of the parents who are half matches, or the siblings, or sometimes in adults you can take their children who are half matches with the patient, and they can be used as a source of stem cells as well. That's called as haploidentical transplantation. And of course, you have a cord blood as well as a source of stem cell. That's called as cord blood transplantation. Match sibling, as I said, 25% will find a match sibling donor in the family. That what happens with the rest 75%? You can either offer unrelated donor transplant, but the chances of finding an unrelated donor for a particular patient depends on how many donors you have in your registry who can you search from, right? So the larger the registry is, the higher is the chances of you finding a donor for them. It also depends on what ethnic mix or the ethnic background of your registry is. So we do not find donors for our patients in registries from US or Europe, although they have millions of donors on the registries. Why? Because our genetic makeup and actually makeups are different than the donors abroad. In our registry, which is a very small registry in India, that is Datri, and a registry which operates from Bangalore also from the BMST, is around 5 to 6 lakh donors. And finding a donor for our patient from that small registry is only about 10%. So that means 25% here, 10% here. What are the rest 65%? Those are the patients where you can offer a half-match transplant from a half-match donor, and practically every patient will have a half-match donor in the family. You have a parent or a sibling or an offspring who is half-matches with you and can be used as a donor. And of course, syngenic transplant is a transplant of identical twin. This is a rare occurrence that you need a transplant and you have someone else to donate for them who's a twin, but if that is the case, that's called a syngenic transplant. Now, where you collect these stem cells from? You collect them from bone marrow, from blood, and the cord blood. And I'll show you, how we do that. This is a bone marrow as a source of stem cells. So, 2 operators on either side, taking bone marrow out from the donor. It's done in operation theaters. It's done under general anesthesia. It takes 1 to 2 hours. And this marrow, which has been pulled out from the bone marrow, is used for transplant purpose. There are some limitations with this as a modality of collecting stem cells. You can collect only 20 ml of bone marrow per kg from the donor, and you need at least 5 to 10 ml of marrow for the patient. And you may have sometimes patient is big, donor is small. There may be discrepancy in the weight, and you may not be able to enough marrow at one setting. You may have to do it at 2 different settings, and store the first aliquot and get another one after some time, after 4 to 6 weeks, or maybe longer than that, and give both the marrow in extracts at one go. Or you can go to this modality, which is called as peripheral stem cell collection. The stem cells as I said, they live on our bone marrow, and bone marrow is the natural inhabitant, a natural home for these stem cells. But you can push them out from their natural abode, and that can be done by using growth factor, GCSF. So if you use the GCSF to the donors, the number of stem cells in the bone marrow increases, and a lot of it spills into the bone, into the peripheral blood. So what happens then after giving 4 days of GCSF to these donors, they come to the outpatient department. It's an outpatient-based procedure. What happens is that the blood comes out of their vein. It goes into this machine. It spins the blood. Stem cells are collected here in the small pouch of blood. You see stem cells, and the rest of the blood goes back into the donor. It's exactly like platelet apheresis. I don't know how many of you have donated platelets. The blood goes out, platelets are collected, and the rest of the blood goes back in. The same way you can collect the peripheral stem cells as well. This is just an example of a kid donating his stem cells. The femoral line is used to take the blood out. It goes in here, it spins here, collects the stem cells, and the rest of the blood goes back through a different vein, and that's how stem cells are collected. That's a peripheral stem cell collection. Now we can also collect stem cells from the cord blood. We know cord blood is a waste product. At the time of delivery, the placenta, the cord blood is anyways thrown away. But you can collect the blood from the placenta and store it in a cord blood bank. And when it's required for a transplant, this is how the cord blood comes to the transplant units. It comes in liquid nitrogen tanks, and you have the small pouch of blood here, which is cord blood, around 30-35 ml of blood. There are two beautiful things about cord blood. One is that it's very rich in stem cells. Second is that it's immunologically naive. It's come from the newborn baby who has not seen the outside world yet. So there's no antigenic exposure to this newborn baby, and hence the graft versus host disease from cord blood is lesser as compared to the mature stem cells, either from the bone marrow or from the peripheral blood. But there is a limitation. The limitation is that although it's rich in stem cells, but the volume of cord blood is very small, and hence the number of stem cells may not be adequate for a bigger sized child or even for an adult. So that is one of the limitations with the cord blood, but this is also a source of stem. So how to overcome that limitations? Either you can use 2 or 3 cord bloods together and give to the patient, or you can also sometimes do something called as ex vivo cord blood expansion. You increase the number of stem cells in the lab and give it to the patient after that. Now that was, we discussed basically a case presentation. We discussed some history of stem cell transplant. We discussed the role of HLA typing. We discussed the types of transplant, and discussed how these stem cells can be extracted from the donors or used for transplant purposes. Now, what would the transplant journey for the patient would be like? So before we admit the patient to the hospital, we make sure that patient is well, patient doesn't have any infections which can get flared up during the transplant process. We make sure that donor is well, donor doesn't carry anything which can be transmitted to the patient, autoimmune disease, for example, HIV infection, for example. So these are the things which are being made sure before we admit this patient to the hospital. Once the patient has been admitted, we do something called as conditioning. Conditioning is basically the destroying the bone marrow of the patient with a cocktail of drugs mainly, but sometimes we'll use irradiation also to destroy the bone marrow of the patient. Once that has been done, you give the stem cells of the donor, whatever the stem cells you have collected from whosoever the donor is, either it's related, unrelated, it's cord blood, it is bone marrow, or it's peripheral stem cells. You give those stem cells to the patient, and this goes as an IV infusion. So there's no surgery involved for the patient. This will be going as IV infusion. And what happens in this condition is that you have destroyed the bone marrow of the patient completely. So there is no bone marrow left in the patient. His white cells, platelets, and hemoglobin become absolutely zero. So you transfuse hemoglobin red cells from outside, you transfuse platelets from outside, but the white cells is something you can't do really much. And after a couple of weeks, there's something called as engraftment. So this is basically the new cells started going up. So the white cells start going up, then the platelets, and then the hemoglobin. And we always hope and pray these new cells which are coming up are from the donor and not from the patient again. And if the patients could start growing up again, that would be rejection. That means you're not like the cells of the donor at all. And once the cells of the donor starts coming back to normal, that's the time we discharge this patient from the hospital. Now, all of us can imagine this is the most important time in the transplant journey. They're left with no immune system at all. And to add to the problems, we have given them conditioning, which is pretty heavy duty, chemotherapy or radiation, and that leads to other side effects also. The most important being mucositis, which your epithelial line of the mucosa of the mouth and the oral cavity and the GI system is all denuded, And to add to the problems, we have got absolute aplasia, no white cells at all, and there's no immune system at all. Hence, they are sitting ducks for infection, a mild infection, which you and me may not be even able to realize can be life-threatening in them, and that's why they have to be kept in special bone marrow transplant wards where you have a HEPA filtered system to, it's like operation theater where the air comes in, which is HEPA filtered. There are positive pressure ventilation rooms, neutropenic diet, and of course very strict 1:1 nursing isolation practices during that time. But when they get discharged from the hospital, things start, when the counts improve, things start getting better, and that's the time when we send them out of the hospital. But the story doesn't stop there, as this again the cartoon showing the same thing, conditioning, counts becoming low, engraftment. But after engraftment, there are some things we still need to follow them up for. One is called as graft versus host disease. Graft versus host disease is the cells of the donor attacking patient's body. And that is what had happened the second, third, fourth, fifth case, which I was talking to you earlier on. That was they developed severe graft versus host disease because they were not actually matched. So if you've got actually incompatible transplants, if they're not matching, for example, or even with full match transplants, you can have graft versus host disease. And that can be acute, which happens a few weeks post-transplant, can be chronic, which can happen a few months post-transplant and a few years post-transplant as well. So we need to follow the cases for this. But there's something called as tolerance which sets in. The patient's body and donor cells get used to each other. They become friends with each other. And when that tolerance sets in, the GVHD and other mechanism doesn't happen. So one of the other beautiful things about stem cell transplant is that they do not need lifelong immunosuppression, unlike solid organ transplants. We give them immunosuppression for a few months to up to a year, and after that they are not on immunosuppression, unlike solid organ transplant. In solid organ transplant, basically you have a lifelong risk of rejection. There's a liver which has come from a donor. Your patient's body has a lifelong risk of rejecting this organ from somebody else. Here, you have replaced their immune system. Immune system has come from the donor now, and this donor immune system slowly gets tolerant to the patient's body, and then you don't require immunosuppression. However, after 1 year of transplant, when they have a complete immune recovery, we need to re-vaccinate them. Their vaccination cover, which they had received before transplant, is all gone, and they re-vaccinate them with all the routine vaccination which we do. So that was one problem, that's acute and chronic graft versus host disease. The second problem which can come is rejection. That means patient's body has not like the cells of the donor, and the patient's own cells start growing up, and that means whatever treatment you are giving for whatever primary disease, it's again back, and the whole process was futile. Now, what are the indications for transplant? Where are the conditions where we can transplant? And these are indications for autologous transplant. Autologous transplant, as I said, you give the stem cells of the patient back to them. Now, this is usually used in malignancies, so probably not the scope of today's discussion, but in malignancies, what happens? When you give chemotherapy to them, their blood counts become low. Hemoglobin drops, platelets drop, and white cells drop. And that remain low for a week or so and then start going back again. If you increase the dose of chemotherapy further, what will happen? You get a better anti-cancer effect, but at the same time, your bone marrow will become more and more aplastic. And if you increase the dose of chemotherapy even further, your bone marrow can become completely aplastic. Your bone marrow will get completely destroyed, and there will be no bone marrow hematopoiesis happening, although you may have delivered a good anti-cancer treatment. So what happens to some of these tumors like lymphomas and brain tumors, even sarcomas? These are all malignancies in children, especially wherein you can deliver them high dose of chemotherapy. But before you give the chemotherapy to them, you take the stem cells, store them, and give it back to them after the chemotherapy has been given. So there's no really transplant here. It is basically rescuing them or helping their bone marrow to recover after chemotherapy with their own stem cells. But allogenic transplant, on the other hand, which is giving somebody else's cells, has got a broader indication base. It's used for malignancies like leukemias and lymphomas and myelodysplasias. Here, the problem is the bone marrow itself. So in these conditions, you cannot use autologous transplant because the bone marrow itself is affected. Leukemia is malignancy of the bone marrow itself. So you can't use autologous transplant. A lot of non-malignant indications wherein use somebody else's cells, immunodeficiency syndromes, hemoglobinopathies, sickle cell thalassemia, bone marrow failure syndrome, storage disorders, and also some acquired disorders like aplastic anemia and PNH. And we're going to be discussing this list a little bit in detail because that's what basically is relevant to us today. So if you see allogenic transplant here, it has got more varied indications. And if you see the list also, this list is a list of deadly diseases where you don't have any other effective treatment option to cure them. Now, in a nutshell, what we discussed in the last few slides is that how does transplant work? Either you can give them high dose of chemotherapy, especially in autologous transplants, and help them to recover faster. Transplant also works as an immunotherapy. So it's, every day in our body, malignant cells are being formed. Every day, all of us, we develop malignant cells every day in our body, but our immune system identifies them and kills them. So malignancy, setting in means there's a failure of our immune surveillance. That means some cells have escaped our immune surveillance and become malignant. Now, when you do an allogenic transplant, that means somebody else's cells are given in the patient's body. These cells go in patient's body, in the patient's body around, identify these cells which are malignant, leukemia cells, for example, and kill them. That's called as graft versus tumor or graft versus leukemia effect. So that's how also transplant works. It doesn't work only as a mode of chemotherapy or radiation you can give them, but it can also work as immunotherapy. And what is relevant today for us, that is for genetic diseases like thalassemia, like sickle cell disease, like other immunodeficiencies. It's a genetic defect, it's a gene defect. So what we're going to do is that we're going to give them allogenic cells from somebody else who has got normal, that mutation is not there, and you replace their cells with somebody else who has got a normal and correct that gene defect. And hence, it's basically a form of gene therapy, although not autologous gene therapy, but an allogenic gene therapy, but somebody else's cells are being used. Now, what are the diseases which we can, in this context today, genetic disease context today, what are the diseases which can be treated and cured with bone marrow transplant? Immunodeficiency diseases is I would say the biggest chunk. I will pardon, but Dr. Meenakshi Bhatt can correct me. The estimation is that 3 to 4 lakh children in India are born every year with immunodeficiencies, and that is a huge number. I mean, we are the immunodeficiency capital of the world probably, and that number is huge. And before, maybe a few years ago, we would not even diagnose them because they will be labeled as sepsis, failure to thrive, and have a dustbin diagnosis of infection, and they would die without any diagnosis, of course. But with better, understanding, with better, infrastructure now to diagnose them both on flow cytometry as well as on genetic evaluations, now we can diagnose more and more of them. And this is just some examples here. I have not put the whole list here, but some of the examples of severe immunodeficiencies, whatever the genetic lesion for severe immunodeficiency is, and Viscott-Aldrich syndrome, these can be cured with bone marrow transplant. There's no other option. There's no other treatment modality which can be used. Of course, gene therapy can be used in some of them, but transplant is a more practical option to cure them. Osteopetrosis, again, a common problem in southern India, especially with consanguineous marriages. It's a very dreaded disease, and of course, a very difficult disease to also transplant in our field. This is the most difficult disease to transplant. For various reasons, but transplant being the only curative option, except for one mutation which transplant doesn't help, but all other mutations, which is about 95% of the disease burden in osteopetrosis from other mutations, transplant is the only curative option for them. Now, this is where we have been collaborating with, I'll show you a couple of slides later on with Dr. Meenakshi here at the Center of Hemogenetics, is mucopolysaccharidosis. When you talk about them, I'm sure you must be reading in your textbooks that enzyme replacement therapy is the way to go. I mean, that is the most ideal and probably the better treatment to be offered for mucopolysaccharidosis. But I know some of you who are working there, you'll understand that arranging enzyme for all of them, for all the conditions, one is not possible, second is too expensive, and to deliver that lifelong is something which is also not possible. So we never had any of this problem in Sydney because most of them would be taken care of by the National Health Scheme, and they will be managed with geneticists. They would never come and see us. But we know that in some of them transplant is an option, and there's a proven role in some of them, especially MPS 1, MPS 6. However, a doubtful role in some of them, 2 and 4. But this is something which can offer them. It's more practical, is one-time treatment, less expensive, and has benefited some of the children, especially if delivered early on. Now, some of you will ask why in the enzyme deficiency would a transplant work? I mean, these are not disease of the bone marrow. These are diseases where you have got a metabolic defect. One enzyme is not being made. So how would transplant work? So transplant works here not by replacing hematopoiesis, but it works by replicating the enzyme which is deficient. So when we do a hematopoietic stem cell transplant, it's not only the hematopoietic stem cells. It brings with it a lot of other reticuloendothelial cells, dendritic cells, macrophages, and other cell types which can produce enzyme which is defective in some of these conditions. So I'll show you some of the data later on for them. Same thing for lysosomal storage disorders, Gaucher's type 1 and type 3, aspartyl glucosamine, Niemann-Pick B and C. These are the ones where there's proven benefit. However, in some of them it may not be helpful. Gaucher's type 2, Niemann-Pick type A. So it's very important also that when we choose some of them for transplant, it's also very important to identify what type they have and whether the type they have can be benefit transplant. Whenever I have a case like this, I pick a phone and call Dr. Meenakshi, do you think that he'll be benefited? We had one glycogen storage disorder, one Gaucher's, where I was thinking that we can transplant the child, but Dr. Meenakshi, no, this enzyme we will not be able to help, and we couldn't do anything for that child. So we need to understand the type, both phenotypically as well as genotypically what type they are, but some of them we can really transplant and help them with this as a treatment option. Same for leukodystrophies, X-linked adrenoleukodystrophy, a very common condition in boys, and and one of the best examples of where a hematopoietic stem transplant can cure the children. Of course, it has to be done early. It has to be done before neurological manifestation set in, because once they are set in, you cannot reverse them. So early referral and early management of these conditions is the crux. A big group of genetic diseases which are macrophage disorders, primary HLH. A lot of primary HLH in our country. Again, some years ago we would not even diagnose them because we didn't have facilities to do that. But now, this is in my practice, almost 60 to 70% of the HLHs which we are seeing in our clinical practice now, especially in children less than 10 years of age, do have a primary HLH component. Congenital neutropenias, reticular dysgenesis, leukocyte defect, Shida-Higashi, ground-granular disease, Grisly syndrome, these are all macrophage defects, genetic defects, where transplant is the only curative option. Bone marrow failure syndromes, again, a lot of burden of this in our country, especially in South India. Fanconi anemia, Schaumann diamond, Biscarotis congenital, nothing else is possible. Nothing else can be given to them. Little bit role of androgens, but that just kind of delays the progression of the disease a little bit, but there is no other way to cure them except for bone marrow transplant. So this is basically a flavor of the different genetic diseases which are, as you saw, the list is pretty serious and life-threatening, and bone marrow transplant can be used. Now, what's happening in our country is that transplants, started early in 80s, but I think the last decade or so, there has been some significant increase in the numbers which are done. 2,000 transplants in 2017, and of course, I've not had the latest data, but we have been doing more than 2,000, 2,500 transplants every year. All the centers put together. This is the data from our registry. But the country of our size, there's estimation that we require 2 to 3 lakh transplants every year. What we are doing is 2,000, 2,500. So we are doing probably 1% of what is required for the country of our size. As I showed you, immunodeficiencies. If we just take the immunodeficiency disorder as a class of diseases, there is estimation that the severe common immunodeficiency is 50,000 to 1 lakh. So that itself will be 1 lakh children who require transplants. Forget the other diseases. Now, what is happening in this transplant which happened in India? If you see this is the pie chart for pediatric conditions. And pediatric conditions, if you see, this is the hemoglobin disease, that's a thalassemia and sickle cell. Then you see here congenital bone marrow failure syndromes. Then you see some immunodeficiencies. So in pediatric diseases, most of the pediatric conditions which are transplanted in India are non-malignant, and almost 50% of them are genetic in nature. And in the last 3 or 4 years now, pediatric allogenic transplants are more than adult allogenic transplants, because our indications are varied, and these non-malignant indications, the numbers of transplants which are done are more. What's happening at our center? This is from my place here in Majumdar Shah Medical Center, Narayana Health City. We've done over 1,600 transplants here. Being a referral center, we do more of allogenic and haploidal transplantation for all the various indications which I listed earlier, including our genetic diseases. This is our experience from last year. We do about 120, 125 transplants. We're the largest pediatric transplant center in the country, again with more allogenic haplotransplants. Now, 2 or 3 disease groups which we have been working on and which are relevant in our setting. One is thalassemia major, where again thalassemia capital of the world, something which we should not be proud of and are not proud of. We have 20,000 children being born every year with thalassemia, intermediate or major in our country, which is a huge disease burden. And of course, stem cell transplant is the only curative option, and gene therapy also is one of the options which is going to be probably available to these children in the times to come. Now, transplant in thalassemia major, this was the Italians started in 1980s, and they published their initial data. That was around 20-year follow-up, about 900 odd patients. What they demonstrated is that almost a quarter of them, 75% of them, can be cured and have a long-term quality of life, which is good. Okay, so that was initial data, 80s onwards, and they also followed the thalassemia kids who did not have transplant. These are the kids who didn't have transplant, and why? Because either they didn't have a matched sibling donor, because that time it was only transplant possible, or they refused for transplantation. And you see the 10 years follow-up, less than 20% of them are alive. So this was proof of the principle that transplant in thalassemia major not only cures majority of them, but also gives a long-term cure and good quality of life, and that kind of opened the arena for thalassemia major as a transplant. But what also Italians showed, that thalassemia major is not one disease. You know, they showed that if the patients are well managed, if they do not have big liver, they don't have hepatomegaly, their iron levels are very good. That's called as low risk or class 1. Versus the patients who are class 3, that means they have big livers, they have got huge iron levels in the body. These are the class 3s. And what they showed is that the class 1s, about 90 to 95% of them could be cured. What they also showed is that class 2s would be something in between, 85 to 88% could be cured. And the class 3s did the worst, that is 75, 78%. So the same disease, but depending on how well they have been managed before transplantation, your outcomes or the chances of cure can range from 75 to 95%. And that's what we see in our experience also here. This is our experience from Narayana Health City, Bangalore. This is a little oldish slide, although we have now completed almost 250, 260 thalassemia transplants at our place. This was class 1s, 18 patients with class 1, only 1 patient rejected, 100% survival, and 96% patients cured in one go. When we look at class 2, class 3s, 135 patients. So this is the irony, in our settings. We see patients advanced, we see patients late, and that is not the case with Italians. They see patients very early, they're transplanted early, they're referred early, and when we see class 2s and class 3s, again 85 to 88% is the chances of cure. So which is exactly what they showed in the data set. But this is something which we reiterate again here, is that thalassemia major, a very common disease, very highly curable disease. Of course, we need to refer them early and manage them well before they come for transplantation. As I said, we do a lot of half-match transplant in the country in our center. This was the same thalassemia patients who do not have full-match donors, 52 of them, and we use a technique called T-cell alpha-beta depletion, and we have this is the data with the haplotransplant. This considers the most complex transplant possible, and about 92% of the patients are alive and well with half-mesh transplant. So if you see, the outcomes of half-mesh transplants are now almost equal to the patients who have a full-match donor. So, so that was thalassemia major. The second largest disease group is primary immunodeficiency disease, and this is our experience for primary immunodeficiency disease, which is again, most of them are autosomal recessive condition, as we discussed, but some X-linked as well. About 37 cases we have done in the last few years. This is their age distribution and all different categories. MSMDs, LRBA deficiency. We have a T-cell functional deficiency, which I ever showed the previous SCID, Wiskott-Aldrich, congenital neutropenia, primary HLH, leukocyte defect. So these are just a mixture of immunodeficiency disorders which have been transplanted at our center. But as I said, this is just a tip of the iceberg. Immunodeficiency is a large disease burden in our country. Unfortunately, most of them go undiagnosed, and sometimes too late for them to be transplanted as well. And this is the type of transplant they have had. Most of them had haplotransplants, because again they lack full match donors, but some of them had full match donor transplants. And this immunodeficiency group also, about 73% of them could be cured from their primary immunodeficiency. And you have to just imagine, immunodeficiencies are the most difficult disease to transplant, because most of them either have a severe infection before going to the transplant, or they have severe failure to thrive, or some other comorbidities before to transplant. And this about 72-73% of the patients who had these severe life-threatening immunodeficiencies could be transplanted. Now this is a lysosomal storage disorder, and I was trying to tell you earlier on that enzyme replacement therapies, substrate, whatever modifications. Some of various other treatments are given depending on what storage disorders you're dealing with, and enzyme replacement therapies, especially for the enzymopathies, and transplant also plays a role. And we have done about 16 or 17 now. This is a little older table I have here. This was about 11 odd transplants, out of which 2 unfortunately didn't make it, but 80% of them could be cured. And I'm very happy to see that all of these patients who have survived, and now I think 15 out of 17 who are alive and well, all of them had enzyme corrections except for one who now has dropped some enzyme after 1.5 year post-transplant. But all the other people, all the other children have had enzyme corrections post-transplant as well. So, something which we need to probably wait and follow for a little longer time, but at the initial goal of transplant, which seems to be enzyme correction, seems to be working well. So, a lot of new things that happen in transplant world. I probably skip this slide, but some of who are from biotechnology background, we do something called as with half-mesh transplants, T-cell alpha beta depletion, a very good genetic, I would say, graft manipulation technique. We all know lymphocytes are the cells in our body which mediate, they give us immune system, but also mediate rejections and graft versus host disease in the transplant context. Now we have 4 types of lymphocytes: alpha, beta, gamma, and delta. T lymphocytes I meant. And alpha, beta are the bad ones. The gamma, delta are the good ones. Alpha, beta are the ones which mediate graft versus host disease, and the gamma, delta are the ones who are the better ones. They help engraftment. They have got antiviral properties. So what we do in these transplants nowadays, half-mesh transplant, you take the stem cells from the donor, you remove the alpha, beta cells and throw them, and give the gamma delta cells along with the stem cells to the transplant. And with this, we have minimized the graft versus host disease almost to zero. None of the patients usually get graft versus host disease because they have depleted or removed already their alpha beta cells. It's one of the largest Asian experience of this kind of transplant. So in my last slide, we discussed how this can be effective, potent treatment, and we discussed how it can help in a lot of these genetic disorders which are pretty common in our context. But however, there are challenges. Delayed referral is one, and this is very important for immunodeficiencies and thalassemia, 2 disease groups where referral done late may not be possible to salvage them. Of course, these are expensive treatments. Lot of these resources are a concern most of the times. Drug availability not a huge concern, but we have got access to everything possible now. Manpower. This is the treatment which is really delivered by nurses. So the nursing care during transplant is something which is very, very important, and that's where we still struggle to have and retain good nursing support to look after the transplant patients. And the last but not the least, I mentioned to you that donor registries. To have an unrelated donor to donate for a patient, you need to have a big donor registry database. Germany has got around 10 million donors in the registry. We, being such a large country and such a large population, we have only 5 lakhs. So to make an impact, we need to have at least 100 million donors on the registry, which is 10 crore people on the registry, to make an impact, so that we can also find donors for our patients at least 70 to 80% of the times to give them a full match unrelated donor. This is the transplant center at Narayana Health Bangalore. As I said, it's very important to keep them in these dedicated transplant rooms during the treatment. Some of the children, some of them have been getting ready for discharge, some of them still in the hospital. We have a strong international collaboration. We see patients from almost 50 countries. There's some of the kids from African subcontinent. This guy is from Oman. There's a guy from Indonesia. And this is a very favorite picture I had this many years ago, I think 3 or 4 years ago, which we have taken. This was basically celebration of 1,000 transplants. You see, most of the people here are children. These are the children, and most of them either 20-30% have malignancies, but other almost 50 to 70% of the patients have some of the genetic diseases, like we discussed here. And if you see, some of them have grown up now, and you see smiling faces, and that's what I think probably keeps us going, because you can make a difference. You can cure 80 to 90% of them can be cured, and can be cured for life, and they become meaningful members of the society once they have been transplanted and being cured of the disease. So thank you very much, and I can take any questions if you have.
Can I ask something?
Yes.
So from your lysosomal storage group, what is the lengthiest time of follow-up for post-transplant that you had with one of your patients?
So if I remember correctly, Dr. Meenakshi may correct me on all this. So I think the first was MPS 6, if I'm not mistaken, and that was in 2014. So that is almost 7-8 year follow-up. So and since then they have been children at varying intervals. The longest would be 8 years, and I think the average follow-up probably, if you take all of them together, would be around 2.5 years, because we've been doing more recently probably than we were doing before.
International group, what is the difference that international group may have with the bone marrow transplant in LSDs?
So LSDs, as I said, West probably in West it's not a very I would say go to treatment or favorite treatment for them at the moment, because enzyme replacement is still I would say better and more feasible and safer. But we don't have that luxury, and I think we have to probably show to the world that in the resource limited settings where this is not possible, this is also an alternative treatment which can be delivered. So I think that is a learning from here. The only problem which we used to face initially, now a little bit lesser than before, that used to come advanced. The one case which I said was the first one, I think 2000, and it's been 8 years now. I remember we did his transplant with NIV. He had a very severe lung disease, restricted lung disease, and he was on non-invasive ventilation for this whole transplant period for 1 month. So what this transplant has only done to him is that probably he's gone off he's not on an NIV anymore now. He's mobile. He is but his is very short. He still has already had a lot of bony deformities which were there before. They're still there. He may require some corrections for some of them neurosurgically. But the ones which are done early, which are done in first, second year of life, they have really done well. So they haven't progressed, and they have really done well from that point of view. So I think that's why it's a little heterogeneous for us at the moment. But those who are done earlier on, they have done quite well.
Thank you for the talk, sir. So I had one doubt. What is the precautions we have to take before the transplantation? Like for any metabolic disorders, you would advise enzyme replacement. Similarly, for immunodeficiency or hematological condition, how do we optimize before we refer them to you, sir?
So optimization would depend on what condition we are talking about. So for example, if I take thalassemia as an example, I showed you how important it is to have their iron chelation, liver size managed. So sometimes we take months and sometimes years to prepare a thalassemic patient for transplant. So if their iron is too high, we need to iron chelate them, get them to very low levels. If their liver is high, transfuse them appropriately so the liver size reduces. So all those things are required to be done. Immunodeficiencies, as soon as you diagnose immunodeficiency, we need to, depending on what immunodeficiency, of course, you are diagnosing, and I'm just talking about the not the humoral immunodeficiencies, which are B cell mediated, which can be managed by IVIGs, which is a different treatment entity altogether. But those ones who are more severe ones, who have got T cell immunodeficiencies, those are the ones. As soon as they're diagnosed, they need to have isolation and practices to be explained to the family. And you must have all heard the bio bubble or the bubble baby who was kept in that bubble for almost 16, 17 years. So that is something to be done straight away. They need to go on some prophylaxis like CMV prophylaxis, like a fungal prophylaxis, like PCP prophylaxis, Septron, and all those things are to be done. And if there's immunoglobulin levels which are deficient, along with the T cell, they have to put IVIG therapies every 4 weeks, and we have to move very quickly. The only transplant which is emergency is immunodeficiency and aplastic edema. These are the only 2 conditions where emergent transplants are required. I remember we have done transplants on ventilators in Sydney, and the patient used to get diagnosed on ventilators. Children are sick in ICU, and we have done transplants on ventilators. That's the only way for them to get better. There's no other way. So those are the important things to be done. Similarly, for as you mentioned, for some of these enzyme deficiencies, and we have now a couple of patients with Dr. Meenakshi and I have been looking after, is that See, most of them we cannot really, either we cannot arrange the enzyme, or it's not feasible. So a couple of them have been able to get enzyme pre and post transplant. So what we try to do is that we give them for at least couple of months pre-transplant and continue for next couple of months post-transplant as well. Because after transplant, the enzyme, this has been our experience in some of the children, is that it usually takes 2 to 3 months post-transplant of the enzymes to come to normal levels. And up to that time, if we can manage them with enzyme resistance, that would be great. But it's not a luxury. It's a luxury. It's not possible all the time. I think only 2 kids who have been able to do it. Others who have not been able to do the enzymes pre and post. You have to answer it yourself, ma'am. But yeah. So Fanconi, yes, a good question. So Fanconi is a systemic disease. It's not only of the disease of the bone marrow. So bone marrow is one of the manifestations. Bone marrow failure is one of the manifestations, but they have other manifestations which are, if I club them to 2 categories. One is congenital anomalies. Bone marrow parameters have become normal, she started at college, everything else, but then slowly the kidney function started deteriorating, and she has gone into which seems to be more likely a kidney failure now, and may require a kidney transplant also eventually. So those are the challenges with Fanconi anemia, and also similar condition like disc-keratosis congenita, they also have similar problems, that they may have lung issues, they may have skin issues which may persist post-transplant also. So those are other associations which can be there and also need to be kind of kept in mind, and that's very important to counsel the families when we transplant them some of these conditions, that there may be other issues which may not be taken care of by a hematopoietic stem cell transplant. All right, thank you very much, and thanks for having me.
Okay. Thank you, sir, for the educative talk, and please accept this memento from Center for Human Genetics. End of the scientific session. May I please request Professor Vien to give a vote of thanks.
Is this working? Mine is the easiest task of this very nice day, which is to say a big thank you to everyone who has spoken, of course, as well as everyone else who has helped in making this event as interesting as it's been. I'll just say 2 other words before concluding, if I may. One, I shall do without risk of embarrassing Professor Sharat Chandra, I think, because I don't see him here, which is to say that on an occasion like this, when we both look back and look ahead, in a place like this, it's worth remembering that it's due to the vision, drive, and persistence of one person, namely Professor Sharat Chandra, that CHG has come into being and has become what it has become. At the time that this was really an idea in his mind that he used to talk over with some of us, and when he first began, Professor Jairam will bear me out, few of us really believed that it would come to the stage that it has. So this vote of thanks really begins with a very big thanks from, I think, all of us here to Professor Sharat Chandra. Then with his online skills, he may not be listening to this, which is also good, because I'll run into trouble otherwise. Then, as I said, we need to look back and look ahead, look at the things that we've done very well, and as today's talk showed, the diagnostics parts of what's happening here and the clinical related parts of what's happened here have been, I think, exceptionally successful by any standards. The bench research part has seen, the lab research part has seen from the speakers, the 3 invited speakers who spoke today, what we can aspire to, and surely we must do that. For the future, I think there are many things to be done, which we've talked about amongst ourselves. And for a place like this, there's no other hope for the future than to improve, than to get better, which we are going to do. I only hope, and I say this from my personal viewpoint, I only hope that we will retain that touch of individuality, quality, and style, all of which has had a great deal to do with the person of Professor Sharat Chandra, by the way. I hope we'll retain some of that while we go in for growing bigger, as we must, as we start expanding both our physical capacities as well as infrastructure and other things, getting more people, expanding space, perhaps going in for funding on a larger scale, especially from central funding agencies. Perhaps we could keep in mind that at the same time we really must retain our sense of difference, really, and see that we don't get submerged into this otherwise seemingly pervasive notion that uniformity, that one size does fit all, must hold good. So long as we continue to do that, I think we are doing well. One of the strongest successes we've had, in my mind, over these past many years, not throughout the decades that we are celebrating, but certainly over the past few years, is our MSc training program and the quality of the students we have succeeded in attracting. And I think that is something that we need to nurture and build up even further in the future. So I'm not going to take more time and stand between you and what I hope will be a good tea. Thank you all very much for coming here. And once again, thanks very much to the speakers, Dr. Bhatt and the other 2 in absentia, for having delivered such splendid talks. Thank you.
Thank you, sir. And as rightly said, Professor Sharat Chandra has been an important and a very important part of the center. We also thank Director and the Associate Director and all the faculties at CHG for making this day a success. I hope you all had an educative and informative session. Tea and coffee is waiting for you. Thank you so much once again.